I'm going to hand over to others in a minute, but I have got some important announcement to make. We try and plan for most things when we arrange conferences, and you might have thought there was plenty of water in Leeds. However, the water in Leeds doesn't seem to be flowing into the toilets in this building at the moment, for which we have apologies. So I never thought I was going to make this announcement at the start of the Bragg Exchange. If you would like the toilets, we can go to the next door building, which is our States building. So I suggest if 100 of you go and press the buzzer on there to go to the toilets, they might actually think there's a problem here. But we will have signage outside. Helen is outside with the stand so we can direct people. Our apologies, but I think as a Bragg team, we're going to say there was little we could do about this one. So with that, having done, I said I would do the toilet information. I'm going to hand over to Claire and Kath for the main part.
Thank you very much. I've just noticed on the slides, Kath, I think we've given you a promotion there by accident. Sorry about that. Welcome everyone to day 2 of the Bragg Exchange. My name's Claire Savvy. I'm Centre Manager for the Bragg Centre for Materials Research. Really pleased to see everybody here. We've got a great set of talks lined up today. Kath is not Deputy Vice-Chancellor. Sorry, Kath, we're going to demote you to Deputy Pro-Vice-Chancellor for Research and Innovation. Really pleased to have Kath here. I'm just going to run through a few other bits and bobs of housekeeping before we get started. The fire alarm test has already happened, so if the fire alarm goes off today, please exit the building. The assembly point is a grassed area just outside the main entrance. First aiders are on hand throughout the event. If you've got any problems, particularly an emergency, that you need to call emergency services, get in touch with one of the Bragg Centre team, and we can help you. We've already told you about the toilets, so ignore that instruction. In terms of where we're running things today, all of the talks will be in this room, and the refreshments, teas, coffees will be out in the atrium where you were earlier when you were registering, if you just came today. We will have posters and lunch in the refectory, which is about 5-minute walks from this building. A member of our team will be walking across there, so if you don't know where you're going, so you can follow them. Just to say as well, if you're not aware, we are broadcasting this live. So if you've got any concerns, just let one of our team know about that. And if anyone is okay with social media, please do tag us on LinkedIn with your exchange experience, whether that's the posters or the talks. We'd love to hear your thoughts on how the event has been for you on social media. And if you haven't already voted for the posters, please do. In your lanyard, you've got a poster voting slip. So you can cast your votes over in the refectory and pop it into one of the voting boxes. And if you haven't already done it, I would encourage you to scan the QR code on the right-hand side. We're really keen to get members' feedback on the Bragg Centre, what we're doing well, what we could do better. So if you want to do that now and save it as an open tab in your phone and do the survey later, please do. It shouldn't take you more than about 5 or 10 minutes. Is anyone holding their phone up? Come on. We'll be sending an email about it later as well. So without further ado, I'm going to hand over to Kath, who's going to give a little bit of an introduction to the session today.
Okay. Thank you, Claire, and a very warm welcome to everybody to the Bragg Exchange. I believe this is your 6th Bragg Exchange, is that right? Something like that? Or 6 years of Bragg. So great to see people here. If you can hear me at the back, you are allowed to come further down if you like. So it's a real pleasure to be asked to do this. I'm actually new in my post as Claire said, Deputy Pro-Vice-Chancellor. I've only been in post for 2 weeks, and this is the second welcome I've done at an event. So I think this is going to be kind of a part of the job I get to do. But it's actually a really nice part of the job. It's something to come and meet communities, see what you're doing. It gives me an opportunity to look through the highlights and the activities that our research centres do, and to understand some of the fantastic work, celebrate the community, and look at what you're doing here in Bragg. I guess to start this, we're in quite turbulent, uncertain times at the moment, fair to say. I don't know, I dread to look at the news. You know, you come out of here, what's it going to say before we've even come out of the end of this session? it does feel like it's quite challenging to keep up with the world. And I think that also applies a little bit to the university sector. We have seen a lot of uncertainty over the past couple of years. You know, we are in a good place in Leeds, but we're not immune to the sector challenges and the financial challenges and some of that. But I think coming to events like this and activities like this, you know, it's very, very tempting to go into a world of doom. But actually, this is a bit of an antidote to all of that. This is a place where you can sort of take that step back. You can think about the science. And actually, to me, it's never been even more important to be able to do that science and engineering and analysis well and build that evidence base that we need to inform how we go forward, to inform policy, to inform practice, to support innovation, and to make sure that we are driving the world forward in that space. Obviously, Bragg is one of a number of research centres and institutes at Leeds, and those are part of our beacons of how we do great research at the university. They are part of that excellence and the way we connect things together, that interdisciplinarity. Those of you from the university will know about the white paper. The white paper explicitly stated that centres and institutes are a really key part of our research landscape and infrastructure and how we want to make sure we drive things forward. And I think Bragg community is one that really exemplifies everything that whole aspect embodies. It exemplifies the values that the university holds, and it also exemplifies that scientific quality, that curiosity, that drive for innovation, and that ability to change things. I've mentioned at the beginning, 6 years I think Bragg's been going for. Over that time, I know it's got a community of 450 people across 14 schools in 5 faculties. So there's a lot of people engaged with Bragg, and of course externally to Leeds as well. And I think, I mean, for me, looking at Bragg, I know Bragg reasonably well, but to look at it and watch what it does and to see that you really drive that strong underpinning science, but you've got that really good, inclusive, supportive culture that enables people to flourish at Leeds. I want to touch a little bit on the research landscape, because I think, as well as the many other things that are changing in our world, the research landscape is changing. And I think there's been quite a notable change in the past 12 months. So we have a new industrial strategy in the UK. We have a new renewed focus around science and innovation from DSIT, and I know we're going to hear from DSIT after I've talked here. And that sort of sets then the strategy where UKRI and the research councils go. And within the DSIT strategy, there are 3 key areas. Some of you might have heard them called Sir Patrick Valance's buckets at events, as we're kind of thinking about where research sits. But curiosity-driven foundational science, how our research and innovation supports strategic government and societal priorities, and then targeting innovative and UK-based company scale-up and growth. And we are expecting that we will see over the next few months the research funding landscape in the UK adjust and tweak to match that, and we're expecting to see greater focus on specialisation, how we support bigger, longer-term initiatives and things. I think Bragg is incredibly well positioned in this new space. So, I mean, change is always a tricky one, but Bragg is really strong in that because Bragg covers all 3 of those buckets. Bragg has absolute, the fundamental science at its core. And by the way, I'm expecting some really good ref papers from you all. But we've also got those really good activities initiatives that engaging externally with industry, with policy, to drive through those societal challenges and that economic growth element of the strategy. And you can see how you're doing this from the sort of training, clean room training, the professional learning piece, through to collaboration, through to things like driving the national agenda. So the example around, I know, Edmund, you've done a lot around semiconductors, around driving that agenda. You've got a really strong fit to advanced manufacturing, to clean energy, to defence and security, to life sciences, all sitting in with the industrial strategy. You've also got a really strong connection to the region. So West Yorkshire Combined Authority, they have advanced materials as one of the key growth areas in them. And I know that Bragg are already really heavily involved in conversations there. I know that they've been involved in discussions about that strategy, but things like participating in a trade mission with a delegation from India. Is that right, Edmund? Yeah. And international stage, participating on a DSIP visit to South Korea, looking at engagement with Vanderbilt University in Nashville, who've got also building a partnership with the city. So there's some really sort of strong connections happening there. So I think you're in a really strong position for being able to do things. I guess one of the challenges, and this is something that I need you all to think about and be agile to, is that we may see some of that money come in different ways. We may see we're going to have to seek slightly different opportunities, and we need to think about how we're agile and how we enable us to respond to those new opportunities out there, which may look a little bit different to the conventional responsive mode activity. I also just want to touch on the next generation. So I think today is a really good place to highlight some of the the dedication that Bragg has and the community of Bragg to supporting scientists within it. And I think that's right through from its inception. It's set out to support all of the researchers, technical staff, and building those, putting those together, those initiatives to support the community. And I think there are two really nice successes to highlight, particularly around PhD training here. So the EPSRC Centre for Doctoral Training in UK Semiconductor Skills, which has been announced very recently, and this is a fantastic opportunity for Bragg. It's going to work with with Swansea University, with 50 PhD students over the two centres, building that skills and technical things. There's also the aligned to Bragg is a new BBSRC, Engineering Biology for Medicine, doctoral training programme, which again will work with King's College and National Physical Laboratory, again supporting new opportunities for students. So there's a real, I think both of those put Bragg's community in an even better position than it was, because that injection to support that next generation of scientists coming through. So very well done to everybody involved in both of those. Back to today, and I think today and yesterday, the Bragg Exchange is it's become a bit of an institution now. It is one of the activities. I've attended it before. It's a great event. I think it goes from strength to strength. I'm told there are 280 people registered for this. We've got 80 posters at it from 11 different schools and 3 different faculties in there. And I don't know how many people are watching, but when I was prepping this, I could see your numbers for last year, and there were well over nearly 450 people who'd streamed last year's event online and in some format. So, it is reaching a lot of people. I'm sorry I can't be there for all of it. I'll stay for the first session, but if it's anything like previous years, you're going to have a really good day, some really good talks, and a big welcome to everybody from here. And I'm going to move on and introduce our next speaker then. So hopefully that feeds you a little bit of intro there, James. So our next speaker is James Penny. James is the Senior Policy Advisor for the Department for Science, Innovation and Technology, or DSIT. And he's going to talk today on some of the government priorities for materials research and innovation. So everybody gets scribbling down your notes as to where this is going. Thank you.
Thank you, everyone. Can you hear me okay? Yes, all good. Okay, so that's my name. First slide. I want to firstly thank Kath, Claire, Edmund for allowing, and the rest of the team at Bragg for letting me come today and speak to you guys, because I think this is really exciting. And I promised Edmund when I first joined the job that I will come up and visit Leeds, and it's taken me nearly 2 years. So I'm glad that I finally managed to find time to come up, and especially for this event, which I think is a really exciting part of the sort of materials innovation calendar in the UK and the ecosystem. So I actually, Kath covered a lot of the stuff that government talk about today, these days, which is the buckets, really important buckets, which I thought hadn't left Whitehall, but they obviously have, which is only a good thing. I'll talk a little bit about sort of what we do in the team, but also sort of some of the strategies and the funding that's going to be coming available as part of some of the work we do. So I'll pass on to the next slide. So sort of advanced materials in HMG, His Majesty's government. What we do as a team, so myself, I am not a materials expert. I am actually a social scientist by background. So when we come to the questions, please don't ask me anything too technical. But really have really enjoyed the last 2 years I've been in this team doing materials. I think it's a really exciting area, lots of opportunities, lots of challenges, but those challenges all have multiple opportunities that are really exciting. I think we can, with the help of you guys here, but across the country, we can meet those challenges and succeed with both benefit to UK citizens and economic growth. So some of the roles we do in DCIT, we're coordinators across government departments. So what we look at is how we coordinate all this activity. There's lots of activity in materials. Materials underpin everything. I think Dave Knowles from the Royce always says that it's materials is everyone's second best friend. It's in DCIT it's our best friend. But I think it's actually a really good way of thinking about it, is that we wouldn't have a lot of nearly all of the innovations we do succeed with if it wasn't for materials that underpin them. Engaging with the community. So this is sort of part of what we do as a team, and I find this probably the best part of it is meeting people like you, people on the ground doing the research, doing the development, and then going on to commercialise and make a success of what they've discovered. I find that really the hands-on approach really the best part of the job. So yeah, we have responsibility. So we're the sector leads in the Department for Science, Innovation and Technology. Pretty new department. So we were created about 3 years ago, from a very big department called BEIS, which was Business, Energy, Industrial Strategy. And we were created as a primary focus for science and tech and innovation across the ecosystem. I think it was a very good decision to do that, because we've been able to have a better think about the landscape and where we want it to go and our ambition as a country. So, and then the other part is responsibility for selling your discoveries, your research across the world, and that's not just in collaborations, joint programs that we fund and through the funding agencies UKRI, but also that's through security, defence, lots of different areas where we invest in materials with other countries that trusted partners that have also innovative ecosystems. The modern industrial strategy. So Kath led to this, and I'm going to talk a little bit about the industrial strategy, the modern industrial strategy, which was published last June, I think. It feels like a long time ago. I think we've just come up to the 6-month anniversary of it. And it's a blueprint for what government is planning to do over the next 10 years. So it's really where the priorities lie. And I've listed all the sort of what we call the sector plans in government, but advanced manufacturing, clean energy industries, creative industries, defence industrial strategy, digital and technologies, financial services, growth and competitiveness, life sciences and professional business services sector plan. So as part of the advanced, and I think how I was on the train this morning thinking about, how do I explain the industrial strategy and the place of materials? So materials is not just a vertical, but it's also a horizontal. So it's not just on its own frontier industry, which is really exciting, and I'm really excited about it, but it also underpins all those other parts of the sector plans, which are really, really important for UK economic growth and for benefiting people everyday lives through technology changes and advancement. So what the industrial strategy set out was a national materials innovation programme. Basically, it's a national approach to how we, as DCIT, want to achieve by the end of this spending review, which will be 2029, it's a 50 million plus programme that looks at primarily translation. I'll come on to what sort of the Royce had done, and I know that Katie Blaney from EPSRC spoke a little about this yesterday, so I don't want to sort of labour it too much, but what that programme is looking at is translation across sort of the mid-TRL levels, so what we call and what the sort of sector calls Valley of Death. What we want to do is provide funding, so a lot of these world-class and cutting-edge discoveries are brought all the way through into a commercial product that we can use, both civil cases, but also defence, which is just as important. And we're doing a lot of work with MOD and DSTL especially on some of this pull-through. Now, what I do want to stress as well is that it's not just about, our focus is not just about translation. We have a really healthy and, I think, exciting fundamental science base in material science, but also the other applications that come off of that. And we are still prioritising that. So UKRI money, this is new money, but existing money that would normally have gone through the research councils will still do that and support the fundamental science, because we understand that it's a value chain that goes from start to finish, and that everyone needs to be supported all the way through that, through interventions, whether that is funds or other support. However that may look. So I've sort of named some of the priorities we set out in the industrial strategy under advanced materials, which was coordination, so coordinating the sector, the ecosystem. I think a lot of work's been done, by centres like the Bragg, but by academics on an individual level, bringing them into a community that talks to each other, collaborates with each other. Someone was saying yesterday about there was I think it was one of the research councils, an old funding call, which was collaborate to compete, and I think that's a really nice sort of a few lines of saying, we need to collaborate, and you can also compete at the same time. Trying to avoid lots of duplication that does happen by working together, and I think that's really at the heart of what we're trying to do. Accelerating those through those TRL levels, really important. Maintaining, and this is one thing, that when we have conversation with ministers, is we want to maintain what's happening already. So the really exciting work you guys do here, the really exciting work that industry is doing, how do we maintain that and making sure that we don't lose our competitive edge that we have in the UK? Because when I speak to and I sort of come on to innovate globally, but when I speak to partners internationally, we really are the envy of the world in terms of research and research quality and research impact. So I really want to stress that's something we want to maintain, but also grow. And I've sort of touched on existing and new investments through UKRI, the new programme, and any future programmes. And I think this is something we want to stress, is that this is not just it. We don't just stop. It's a moving process, and when we come around to the next spending review, we think about, okay, well, we want to make a big bid, and this is the evidence for proving what the money was spent on last time and what the impact was. So that's really, when we talk to researchers, and I hope that you take home from this is that this isn't just it, and we're an open door as well in DCIT. We really welcome feedback, and I'll be here the rest of the day to answer any questions and have chats. So really welcome that. So yeah, touch a little bit on this. I didn't want to do too much on this, because I think that probably Katie may have touched on it yesterday in her speak from EPSRC, but. Government really championed the efforts of the Royce Institute, and actually it's not just the Royce Institute, it's the community at large, and this is what we see it as a sort of a community innovation strategy, and you can see on the picture we've got over this side Lord Vallance, who's our science minister in Department for Science, Innovation and Technology, real champion for materials, but also a champion for those three buckets and fundamental science, which is the most important part. I've put some over 2,000 experts, so it was a real community-led strategy, and that's really helped us in coalescing the community, but also when we go into ministerial office or very senior civil servants we speak to, we're saying, this is the community, this is the value of the community, and this is where we want to go with the community. And that wouldn't happen if it wasn't for your good selves. I think that's all I sort of wanted to talk about, and I wanted to sort of open up to any questions people may have. It's still a very much an ongoing sort of journey. We've just had a call that closed, I think it was for 2 million under the National Materials Innovation Programme. That programme's still being designed as we sort of look at where best we can make those investments. But there was a call that was closed, I think it was beginning of January or maybe the end of December, I can't remember, but do watch out for things like that on both EPSRC's side, but more importantly, Innovate, where the translation part is happening. And yeah, really looking forward to the rest of the day and to listen to some of the exciting talks. And yeah, so any questions?
Right, got any questions? Please stick your hand up. I've got a very amazing helper here who can run to you with a mic.
Hi, thanks for the talk. Katie Blaney from EPSRC spoke about the industrial strategy yesterday, and I'm at risk of boring my colleagues by asking a related question. Has the sort of 8 themes, and advanced materials is under manufacturing. I think you're right that it does underpin many of these other areas. It's hard to imagine our ambitions in defence, life sciences, clean energy being realised without advanced materials breakthroughs. So how is that sort of put into practice? Because I could imagine if I was kind of tasked with being the person taking care of life sciences, it would be easy to sort of think, oh well, I'll just let the advanced manufacturing person deal with that, where really I should be paying attention to it.
Yeah, thanks for that question. So that is one thing that what I'm here for, and what my job is over the next few months, but also the next couple of years, is making sure that all those activities and all that money that would be going into something like life sciences, take life sciences as an example, I'm knocking on their door to say, well, what have you considered the materials aspect to it? Now, I think I want to emphasise how important that being a frontier industry under advanced manufacturing is, both for unlocking investment, but also unlocking attention, sort of signposting as well. I think this is one of the other things, is signposting that it is a priority, both for investors, industry, and the research base. But it means that also we leverage from other departments. So advanced manufacturing sits within the Department for Business and Trade. We're in Department for Science, Innovation and Technology, 2 different departments, but we both have to work together to leverage funding from both departments to invest in materials innovations. What we've got is a materials innovation leadership group. So that's a group of senior stakeholders that are looking at exactly this question of how best we access other money from other application areas, so take life sciences, in their funding calls. And this is something, so on a level on my level, we're talking about, okay, we've just had this, we've got this money available, what should it be spent on? Well, we need to go and speak to everyone who's a frontier industry, including advanced materials. What should it be spent on? And then we incorporate it within what our priorities are laid out in the industrial strategy, but also what's in our sort of, in our materials program. So we try and align them. So there is alignment, and I understand, and I think, what EPSRC are doing and what Innovate and UKRI as a whole are doing is following that sort of, following that blueprint as well of the industrial strategy. It's an industrial strategy for the whole government. DSIT are the home base of UKRI. So making sure, we do leverage that, and that is really important. I think we're not forgetting that materials don't exist in the other the other areas, and it's important that we don't forget that. But I think for what we saw was the opportunity of getting ourselves named as a frontier industry was really important, keeps us at the table when thinking about all sorts of different things. It's now government policy, and it's one thing that we strive for, and we hope the community and the ecosystem also strives for. So yeah, thank you. I hope that answered your question. Just yeah.
Sorry for coughing. Any other questions?
Thanks, James. I was interested in when you mentioned translation, and forgive me because I'm old and I'm getting more and more cynical. But what is it going to be different from the previous, let's say, decade, where again there's been an emphasis on translation? People said that's what we're really bad at. So what is it that's going to be different?
So I think what we haven't thought about, well, what I think has been missing in what us and the research councils and UKRI more generally think about is that where EPSRC funding goes, and then there's a sort of a hole between that and Innovate funding, the mid-TRL levels. What this money will do is we want to unlock that opportunity of bridging that valley, and that starts right at the beginning in the fundamental science. So we were talking to Edmund earlier, and I was talking about some of the really good work that Bragg are doing about commercialization and how we get those researchers and that research right at the beginning to think about where that application may be, pulling it through or pushing it through, depending on what that technology is. And whether that's through government money, whether that's through a mixture of government and private money, lots of different opportunities. So I think that's really where we're focusing on is where the funding doesn't exist, where we can fill, where we can put money. And this is still very hypothetical because there's lots of decisions to be made about the programme specifically. But this is what we laid out in the industrial strategy about how we get those discoveries, these world-leading discoveries in the UK, to stay in the UK, to manufacture in the UK, and to grow in the UK, and that's really where the value we think lies, and how do we support you guys as the people on the ground discovering this stuff and doing the research, doing the development, how we can support you through to commercialization. I think that's what we mean by translation. I hope that also answers your question, or if you want to follow up.
I don't think it's only about money. It's about capability as well and access to that capability. So how do you join up what's going on in academia with the catapults, with Innovate UK, with access to industrial laboratories that can do the scale up? And I think that's where, in my own experience, where there's a huge gap.
Yeah.
So it's not just about the money, it's about changing people's perception, making sure they have access to these facilities.
Yeah, and also so that is, I would say it's exciting to get new money, but it's a very modest fund of money. So our other priority is how we better coordinate across the community. So like the work that Royce have been doing with the strategy, but making sure that we have access to, because we've got brilliant facilities across the UK that in a lot of places are being underutilised, I think. So how better we bring in industry, bring in academics to existing facilities, existing infrastructure and resource, to better achieve what they want to do. So no, I take your point, and I think it's a good one, and one thing we're thinking about. So it's. Yeah, we're thinking about how best we coalesce the community, and part of it is engagement, but the other part is understanding, what we have been doing is a stock take of what is in the UK, what's happening, where's the activity happening, and how best we can support that, not necessarily through funding. And that's always a good point, is that it's not a endless pit of money that we want to, and there are other levers we can use as government, as research councils to better achieve our aims.
I think we'll end it there. Thank you very much again to James.
Thank you. do catch me if you have any other further questions. I'm happy to.
Yes,
to
James
answer.
will be.
Thank
You're
you.
here all day, aren't you?
Yes, I'm here all day. Yeah.
Hi, I'm Fiona Meldrum from the School of Chemistry, and I'm chair. Okay,
Hi.
so our next talk today, we have Professor Leon Black from the School of Civil Engineering here in Leeds. So Leon is an analytical chemist by training, where he did his PhD in Bristol on the development of patinas, so that's the surface covering of architectural lead. He then took quite a change and went to Germany to work on nuclear materials, and then returned to the UK to Sheffield Hallam University as a research fellow, and then to the University of Leeds, where it says rather poetically here, he remains to this day. So his research over the years has moved from applied analytical chemistry to understanding the interplay between the composition, structure and function of cement. And he is ultimately using his expertise now to understand how we can make materials more durable while minimizing environmental impact. So Leon's talk today is going to be on achieving circular concrete.
Okay, thank you, Fiona. Okay, so good morning, everybody. Pleasure to be here. I'm talking today about a material. I looked at the list of all of the presentations over these 2 days. I can comfortably say I'm talking about the material with the lowest economic value, but equally, it's a material that is heterogeneous. We know it contains defects. We know that it can, well, we all know about structural problems with concrete, but equally, it's a material which underpins modern life like nothing else. Okay, we use 4 billion tons of Portland cement every year. That's equivalent to about, wobbling about, I know I've put on weight, I'm not causing the entire thought. Christmas, and I'm causing the screen to stop to wobble. We use about 1 cubic meter of concrete per person per year globally. Okay, that comes with an environmental cost. Okay, cement production is responsible for about 8% of global greenhouse gas emissions. If the cement industry was a country, it would be the 3rd largest emitter in the world. Okay, now I'm not going to stand here and say that we have to do without cement, because if nothing else, I'd then be out of a job. But it's how can we use this ubiquitous material more effectively. And what I've done, like I said, I've spent 20 years looking at how we decarbonize, how we make concrete durable. In recent years, I've then also been saying, well, how can we move away from our current approach to construction of we build something, we use it, not just construction, actually, it's life in general. We build something, we use it, we finish with it, we throw it away. Okay, so how do we make concrete more circular? Okay. So if we look at C&DW, this is construction and demolition waste. In the UK, we produce 68 million tonnes of this per year. If you then look at official statistics, 92.3% of this is recovered, repurposed, recycled or reused. That's wonderful, aren't we being green? No, what we're doing is we're taking this material and we're burying it and using it to fill holes in the ground. We're using it as subbase on which we will build new roads. We're using it every time you go to a shopping centre and you wonder why the car park has a nice hill with some trees planted on it. That's reusing construction and demolition waste. Okay? It's landscaping. It's also avoiding the £30 gate fee for landfilling it. Okay? So it's been downcycled. We can do something more effective. Okay? So we can transition from a linear to a more circular economy. Okay? And the starting point for my work on this was this quote by Thomas Rao, who's an architect, then formed the company Madasta. And it's waste is material without identity. Okay? This was my starting point. If all we know about construction and demolition waste is, all we know is that it's, you bring a building down, you demolish it. you've got a lump of concrete this big, say. If all we know is it's this big and it's stiff, that we stand on it and it's not going to give way below our feet, we use that identity. We use it to fill a hole that's this big, or lots of it to fill a bigger hole. We use it to stabilise the ground such that we can build a road on it because we know of its strength. But that isn't effective. So what we want to do is say, well, how can we improve this recyclability or this reusability of concrete? So this is some crushed concrete. Okay, this is some aggregate. For just a quick whistle-stop tour. Concrete contains cement paste, so cement and water, sand and coarse aggregate or gravel. Okay, and it forms this heterogeneous composite. This is some gravel. This is some cement paste that's stuck onto it. Okay, very simplistic terms. And the more you process this material, the more you take it from this roof above our heads, to lumps, to small pieces. If you were to cut through this, and do this schematic here, you will see you have your original aggregate and you have cement paste stuck to it. And the important factors are, what I want to point out here, this ITZ, which is the interfacial transition zone. That's the interface between, when you're making your concrete, your fresh cement paste, so your cement and water that's in a plastic state, and the surface of your aggregate. That is a point of weakness, because if you do characterization on this aggregate and you look at its porous, this ITZ, it is more porous and it has a slightly different mineralogical and chemical composition than the main bulk of the cement paste. So this ITZ is a point of weakness. And in recycled aggregates, you've got an ITZ here between the original aggregate and the old adhered cement here, and you've got a new ITZ between the adhered cement or the recycled aggregate and the fresh cement. Okay? And understanding this ITZ is important for improving the reuse potential of post-demolition concrete. So what is recycled concrete aggregate's identity? As I've said, we know that it's inert, relatively, okay, because it exists within the concrete that we have just brought down in a building. We know that it's dimensionally stable, and therefore, with that identity, that's why we use it for backfill, for landfill, or for landscaping and such like. We also know that this adhered cement paste is problematic. And what we did, this was Ali Al-Janabi, who's a PhD student just finishing with me. We took some concrete. We took a 5-meter concrete beam that had been used as part of a different PhD project by somebody else within the department. And we said, okay, let's reuse as much of that material as we possibly can. And we started off, we crushed it, little more than sticking it through a jaw crusher, and then processed it, which was little more than sticking it in a concrete mixer with no water, for half an hour. And over time, that just abraded the surface a little bit. Broke up this large composite into smaller pieces. Then we did a sieve analysis, and you have, this is natural coarse aggregate, natural fine aggregate, hardened cement paste, recycled coarse aggregate, recycled fine aggregate, recycled concrete powder. This came about as a sieve analysis. Coarse aggregate is anything above 5 millimeters. Fine aggregate is between 125 microns and 5 millimeters, and the powder is anything less than 125 microns. We then dropped it all in acid. Okay? We're fortunate in Leeds in that all of the aggregates that we use are quartz, all the sand we use is quartzite, and cement paste is alkaline. Okay? That bit is universal, not just in Leeds. We dropped it in acid, that dissolved away all the cement paste, and then we could work out so how much of each of these size fractions was cement paste, how much was aggregate. And you can see there's a little bit of this adhered mortar. That is what causes a problem about the reuse of recycled aggregates. So wanting to give this recycled aggregate a bit more identity, this is just the crushed material. This was after processing. It doesn't look very different. I can fully understand if you're looking there and going, there is no difference between those two. Trust me, there is. Okay? But then we started to look at water absorption capacity. How much water does this aggregate take up? And this is related to the amount of cement that's adhered on the surface. So your quartzite aggregate is impermeable, the cement paste is porous. The more cement paste you have as a proportion of your aggregate, the more it takes up water. What that reflects is also the problem around this interfacial transition zone. So we started to do various bits of characterization on these aggregates. So again, taking water absorption capacity. This is against aggregate size, so whether it's coarse aggregate, fine aggregate or not. And hopefully, conceptually, you can understand if you have a piece of aggregate that's, say, got 1 millimetre of adhered cement paste all around its size, the proportion of cement paste increases as that underlying aggregate gets smaller and smaller. So as you decrease your aggregate size, your water absorption capacity increases. For a concrete technologist, that's important. Okay? High water absorption capacity is a problem because it messes up your concrete when you've got it in its fresh state. So we then thought, well, how can we improve this? One of the things we did, we simply carbonated it. Okay? I mentioned that your hardened cement paste is alkaline. So while we used it to then use that alkalinity to dissolve it in acid, we could also get it to react with carbon dioxide. Act almost as a carbon sink, taking back some of that 8% of global CO2 emissions associated with the cement industry. And when we carbonate it, you convert the calcium hydroxide, which was within your hardened cement paste, you convert that to calcium carbonate. That densifies this adhered mortar, and your water absorption capacity decreases. Okay? That was great. That's where Ali was, and we said, okay, there's some promise here, but we wanted to take it a little bit further. Ali then, we made some concrete with these materials, replaced the entire, so just over, density of concrete, about 2.4 tons per cubic meter. Of that, about 1,900 kilos is either coarse or fine aggregate. Okay? We replaced all of the coarse and fine aggregate with the recycled material, control mix, and then we recorded concrete properties. Okay? First thing that you measure as a concrete technologist is the slump. Okay? Nothing more advanced than an inverted cone. You fill it with concrete, you lift the cone and measure how much it falls under its own weight. Okay? It doesn't sound technically, it's not technically advanced, but it's incredibly important because any contractor who's on site building something wants their concrete to flow like water. Anything less than that, and it's a problem because it takes longer to construct your buildings. Okay? So our control mix had a slump of 140 millimeters. When we used recycled aggregates, it dropped. That's because the recycled aggregates are porous. They take up some of the water and stop that water lubricating the mix. So we added a super plasticizer. This is just an organic addition to the concrete that breaks up some of the flocks that form within a fresh cement paste. And we can regain that slump. That's important because, like I say, contractors want concrete to flow like water. What we also found, however, was that as we replaced the natural aggregates, the control mix, with recycled aggregates, the strength generally was about the same, even increased, particularly by 28 days. Okay? This sort of runs counter to what a lot of people say around concrete. This interfacial transition zone is known to be problematic. It decreases the strength of recycled aggregate concrete. So we were thinking, well, what's happened? Well, the first thing is, once you've crushed your concrete, you've got a more angular material, so you get a better interlock. That improves the strength. We also think that the increased porosity of the recycled aggregate is actually beneficial. It takes up some of the water from the fresh mix. That decreases what's known as the water-cement ratio. And as I tell my undergraduate students in the lectures on this, if you remember only one thing, it's that as your water-cement ratio decreases, the strength of concrete increases. Schematically, the cement particles in the fresh state are closer together, therefore they react more and they produce more of what's known as calcium silicate hydrate. It's the main binding phase within Portland cement. It's the built environment's glue, holds the roof above our head. Okay? So this porosity decreases the water-cement ratio. The problem was, we showed that the carbonated material performs better. That's a material that doesn't have the same water absorption capacity, so it can't account for the increased, can't account for a decreased water-cement ratio and therefore a higher strength. So we started to do some characterization. This is the surface of recycled aggregate. After carbonation, pretty ill-defined. There's not really much to see there. However, here we've got the formation of calcium carbonate crystals. Okay? That's densifying the surface of your recycled aggregates. We then put it in fresh concrete. Here you can see this is aggregate. This is the fresh cement paste. This is our recycled aggregate. There's voids here. That's your interfacial transition zone. Once they're carbonated, you can just about make out the carbonated adhered mortar here. And it, to an extent, trust me on this, it improves the properties of this interfacial transition zone. But it's more than that. We then looked at the properties of, this is concrete powder and carbonated concrete powder. We did thermal analysis and infrared on this. Calcium hydroxide concentration, we can determine from this mass loss at about 450 degrees. About 5.5%, just under, of calcium hydroxide within the fresh recycled concrete powder. Drops about half of that after carbonation. Okay, it doesn't fully carbonate because the calcium carbonate forms a skin around the outside of the surface and stops, so reduces the rate of carbonation to the inner material. The original material also had about just under 4% calcium carbonate. Okay? Now, if we take this amount of consumed calcium carbonate and turned it into, we'll say, how much calcium hydroxide, how much calcium carbonate can this produce? It can only produce about 3.5%. However, when we characterize this, we had almost 15%, this mass loss here. Something was going on. There was another source of calcium to produce calcium carbonate. The evidence for that was, first of all, a lower onset decomposition temperature in the thermal analysis, and also a shift in these FTIR bands. These are our silicate bands. This is characteristic of calcium silicate hydrate. This is characteristic of a decalcified calcium silicate hydrate, as is that earlier onset temperature. We pulled calcium out of this built environment's glue. We turned the surface of our aggregate into a mixture of silica gel and calcium carbonate. The cement industry are really interested in this material. I'm going to point and say thank you to Kai Wan, because these are her results here, actually. The cement industry are really interested in this because this mixture of silica gel and calcium carbonate is being used or being put forward as a potential supplementary cementitious material. They can replace anything up to about 20% of cement with this material, and it decarbonizes the cement industry. Okay? And we confirmed that because when we did the test, this is a standard test. It's a strength test replacing 20% of your cement with this, with whatever you're testing. A threshold of 75% of the strength of your test against the reference material is good enough. The as-received material has a strength activity index of just over 60%. Once we've carbonated it, it goes above this 75% threshold. It's reactive. But what we were seeing was it was happening on the surface of the aggregate. Okay? This is, get this. This is recycled aggregate. This is the cement paste. This is the carbonated recycled aggregate and a cement paste. Okay? The backscattered imaging, we can make out the really dark grey to black areas here. That's porosity. This mid-grey here, that's a decalcified calcium silicate hydrate. But we can use this to try and quantify the porosity of the material. Again, backscattered imaging, taking a segmentation, or taking the aggregate, then a thin strip here, segmenting it, and looking at the grayscale within that segment, we can determine the porosity at a given distance away from the recycled aggregate. Natural aggregate, there's a broad, porous interfacial transition zone. As you carbonate it, you densify this material. You also make a reactive surface on your aggregate that improves the performance. So in conclusion, we need to do something more than burying construction and demolition waste. We can use it. Additional processing improves performance. Carbonation particularly improves performance. The next thing is, how do we look at non-technical barriers? I'm going to thank those people who've basically funded me and who've done the work. Particularly want to mention this S3. This is Safe, Swift, Sustainable Reconstruction of Ukraine. It's a project we've been working on for a couple of years about saying, well, what do we do post the illegal invasion of Russia, of Ukraine by Russia, and the significant quantities of demolition waste that have been arising there, looking at how to reuse that. Thank you.
Okay, we've got maybe time for one or two quick questions.
Just thinking back to yesterday and Ming Wen's talk, wouldn't it be good to do a nano indentation map across that interfacial transition zone?
Yes, yeah, it would be. We have done similar stuff with nano indentation. There is a problem because concrete is so heterogeneous anyway that there is a risk that you lose. It's lost within the noise. You know. But yes, it is an option.
Yeah, I didn't realize that cement was so fascinating, but it is.
Yeah, thank you.
Yeah.
Okay.
The recrystallization at that interface is really very interesting, and I hadn't appreciated the fact that actually you need the least amount of water possible to make the best cement. Now, calcium carbonate is quite different, right? It's rather soluble. Do you think that the reason this works so well is because calcium carbonate has high solubility, so it's easy for it to recrystallize and fill in an interface like that?
No. Calcium carbonate plays an important role. It is present. It doesn't dissolve in the fresh state. It's there. It acts as a nucleation site. Other work that's been done elsewhere shows that it acts as a nucleation site to initiate early stage hydration of the fresh cement paste.
I see. Okay.
So that's what it does. Longer term, it does react with some of the components within the cement. Again, I could talk about it for hours.
There's a lot known about how to modify the behavior of calcium carbonate in its dissolution crystallization. I wonder if any of those tricks have some role in improving this further, or maybe it's not needed because it already works well.
Yes, you primarily end up with calcite that's in there because of everything else that's going on. You're up at pH 12.5.
Yeah.
The aqueous solution, I've done lots of work on carbonation of cements. In the lab, we see all sorts of fancy things. Generally, when we then look in the field, you only ever see calcite.
I see.
That's
okay.
Okay. I think we have to move on in the interest of time, so let's thank Leon again.
Okay.
Very important announcement today. The water is back on in the building. We can use the toilets now. So, thank you.
Okay. Our final short talk in this section is from Andrea Laybourn from the School of Chemistry. So Andrea got her PhD at the University of Liverpool, where she was looking at the synthesis and characterization of amorphous porous polymers, principally using solid-state NMR. She moved to the University of Nottingham as a research fellow, where she was awarded a Barrow Award from the Royal Society of Chemistry, and then a UKRI Future Leaders Fellowship. Then she joined the University of Leeds in 2025 as an Associate Professor of Sustainable Materials Manufacturing, where we all benefit from her enthusiasm and obvious love of life. Her research interests lie within ultra-fast materials processing using microwaves and continuous flow and automated technologies. And she's particularly interested in the sustainable production of functional materials. So her talk today is diving into porous materials in the pipeline, optimising metal organic frameworks in flow.
Thank you very much, Fiona, for the kind introduction, and thank you to the organisers for organising such a wonderful event and the invitation to talk to you today to give a snapshot via a case study of the research that we do within the group. So as Fiona mentioned, I'll be focusing on porous materials, specifically metal organic frameworks, and looking at how we've optimised these and their hybrids using flow technologies that we've developed in the group. So metal organic frameworks are porous materials. You can think of them as porous sponges, and they are composed of metal nodes and organic linkers, which come together to give these framework structures with lots of free space within them. And because of the metal node and the organic linker, you can think of them as Lego with lots and lots of different combinations, leading to a wide variety of different structures. If you modify the nodes, you can get lots of different structures, and if you modify the organic linkers, you can get lots of different chemical functional groups within these materials. And so they are very, very tailorable and can be tailored for a wide variety of applications, from things such as gas storage and separation to water harvesting, for example. And so there are over 100,000 structures in the CSD at the moment for these materials, and this is increasing. And the importance of the field of metal organic frameworks was recognised last year through the award of the Nobel Prize in Chemistry. So metal organic frameworks are clearly important materials. However, they can be quite challenging to make, and this can be energetically challenging to make, but it can also be challenging in terms of reproducibility and scalability. And this is something that we are interested in addressing within the group, and we're interested in using a range of flow technologies, microwave technologies, and more recently, automation to address these issues in reproducibility, optimization, and enabling rapid optimization, going from years to hopefully weeks, and the reproducibility and scalability of these materials. So today I'm going to focus on one particular metal organic framework, given the time, and showcase how we've used flow technologies to be able to scale this whilst maintaining the properties of this material across the scales. So the particular metal organic framework that I will be showing is UTSA-16 zinc, which is shown here. And this is synthesized from reaction of citric acid with zinc acetate, which is advantageous because these are relatively cheap materials. And you get the UTSA-16 zinc structure. And our interest in this material comes from its CO2 uptake capabilities. So this is why we were interested. So this material had only been made in a batch process prior to us developing our flow systems to look at it. And so what we did was we developed a countercurrent reactor, which is a nozzle going down and a nozzle coming up, and you interface your reagents within that particular section of the system. And then you have a zone afterwards where you can hone in on the crystallization. So you're able to focus in on the nucleation here and then the crystallization. And you can heat either conventionally within these zones, or you can use microwave heating as well, which is also advantageous because you can play around with the kinetics of the reaction and the kinetics of the crystallization. And I should say that Luke Woodliff was the PhD student in my group who pioneered this work and led this work. So at this particular time, the reactor that we developed, it doesn't have any automation or feedback loops. We're looking to address this now. So this work was done one factor at a time, optimization, which took a very, very long time. But we were able to see some very interesting results. So first of all, we varied the zinc to the linker to the base of the reaction and found 1 to 3 was the optimum in terms of the yield and the CO2 uptake. And then we played around with the flow rate within that flow platform. And we found that there was a sweet spot roughly around 70 to 80 mils a minute in terms of both the yield and the CO2 uptake capacity. And we believe that this is due to the rapid mixing and optimum mixing with that flow rate in that nozzle-in-nozzle reactor. So I mentioned that we also were able to separate somewhat the crystallization of this material. So we had a look at changing the temperature of the post heater to have a look at the effect on crystallization for this. And we found that as you increase the crystallinity with increasing temperature, you get an increase in your yield and you also get an increase in your CO2 uptake capacity as well. So more crystalline material gives you a better CO2 uptake. And to give you an idea of the production rates that we're able to produce this material on, we're up at 173 grams per hour, which is a 77-fold increase compared to the previously reported batch syntheses. Now, I mentioned that this material is particularly interesting for CO2 uptake, but metal organic frameworks, they're able to take up a lot of CO2, but the free space within their structure is a disadvantage in terms of the thermal conductivity. So if you've got a lot of free space, you're going to be very poorly thermally conductive. And so our idea to overcome this was to embed magnetic nanoparticles, specifically magnetite, within the material to be able to use induction heating using a magnetic field to overcome this thermal conductivity issue. So we thought we could use the magnetic field to heat the framework and then cause that to desorb the CO2. And this is known as magnetic induction swing adsorption. So what we did was we took iron oxide, which had also been produced within the group. We coated this with citric acid, which is the linker. This allows good adhesion of the metal organic framework to the magnetite nanoparticles. We placed these inside the reaction mixture, and we flowed this into the system, again with ethanol acting as our anti-solvent to nucleate the formation of this material. So what we found when we added the magnetic nanoparticles is that you don't get any detrimental effects on the yield, so the yield is maintained. And you can also get the same CO2 uptake capacity, which is quite key because it's showing that the magnetic nanoparticles are not blocking the faces of the pores. They are at 20 nanometers, which is much larger than the pores of the MOF, which are at 2 nanometers, so that they don't go into the metal organic framework. So we can create that composite with the magnetic properties without blocking the surface area or the porosity of the material. And we wanted to have a look at how well distributed or not the magnetic nanoparticles were in this composite. And so we used EDX with mineral liberation analysis to be able to look at that. And you can see from these images that we do get good distribution or excellent distribution of the iron oxide nanoparticles in our frameworks. And again, we were able to produce reasonably high production rates of around 150 grams per hour for this material. So as I mentioned, we were interested in the CO2 uptake capacity, and so we used thermogravimetric analysis to look at the CO2 uptake of this across a few cycles. Luke has since gone on to do a doctoral, a PhD plus, or a doctoral prize fellowship, and has since extended this many times beyond 10 cycles. And so we can see that you've got good CO2 absorption and fast release as well. And then what we did was we had a look at whether we could heat the material using an induction heater. And so you can see that the framework without any magnetic nanoparticles in, it doesn't heat in a magnetic field, which is what you would expect because it's not a magnetic material. And then as you increase the content of the magnetic nanoparticles, you can get much, much more rapid heating profiles for this framework. And so to give you an idea, the temperatures was specifically within the laboratory. Yes, it will change in industry, but you can get up to 60 degrees, which is the temperature that we're interested in to desorb the CO2 within 10 seconds using this induction field. So that leads me to conclude the work today, saying I have used a case study of our work to show you the benefits of using flow technologies. We're also interested in coupling this with microwave heating to play around with the reaction kinetics. I've shown you the continuous flow synthesis of UTSA-16 zinc and a hybrid material of this that is magnetic. And we're able to achieve between 150 and 170 grams per hour for this. And as I mentioned, this optimization was done one factor at a time. So we're now incorporating automation and feedback loops to enable much, much more rapid optimization. And we're extending this to a wide range of different metal organic frameworks and applications. So I'd like to say a massive thanks to the research group, the Motley crew, collaborators for this particular work as shown here. A massive thank you to them. A huge thanks to the School of Chemistry and IPRD at Leeds, who've been incredibly welcoming since I started here last year, and the funders for funding the research. Before I finish, I just want to highlight that this is a snapshot of our research. At the core is synthesis, but we're also interested in a wide range of applications using these tailorable materials. So I very much welcome opportunities to discuss this further and collaboration as well. So thank you very much for your attention.
Okay, we've got maybe time for just one quick question.
So this is really interesting. Can I ask this, what you're doing in the lab, how easy is that to translate that into an industrial sort of pilot line or production line or whatever? I'm not quite sure of that connection part.
Sure, yeah. So we're using a range of different platforms. With the platform that I've shown, this technology has been realized and you are able to produce ton scales for certain metal organic frameworks. It's an industry-proven technology, this one. So Promethean Particles is the company that has taken this forward and used that technology to make MOFs.
Okay, really quick.
Thank you. That was a really great talk. Have you looked at how much energy you're taking to release the CO2 compared with, let's say, the MOF that's currently used in the commercial application?
That's a really, really good question, and I'm afraid I don't know the answer to it in terms of the absolute quantities of energy. So I think research, certainly from our point of view, the research needs to be done within that area to make that comparison. I do know that we would anticipate that it would be far less using the magnetic induction swing absorption because of the energy. You would need far less energy to use the magnetic field to release the CO2. But in terms of exact quantities, I'm afraid I don't know any further beyond that. But it is a fantastic question.
Okay, let's thank Andrea again.
Right, I think maybe we'll just give people 5 minutes because I appreciate we're going straight from one session to another. If you need to go to the toilets are working. This is your moment now. So you've got 5 minutes really quickly while we get everyone set up with mics for the next session.
Okay. Hello and welcome back to the final session for this morning. My name is Ardian Marina. I am the Director of Institute of Functional Surfaces here at the School of Mechanical Engineering, and I'm delighted to be chairing the session on functional surfaces. It is in the next an hour, is it an hour? Yes, 1 hour or so, we'll have another set of 3 presentations with a focus on surfaces, covering various topics on surfaces, kind of demonstrating the broad, wide range of research innovations on this research theme. So it's my pleasure to introduce the first speaker, who is Louise Gale from Royce. Louise started her academic career at the University of Cambridge, after which she joined Rolls-Royce, where she is now a material specialist in the Future Technologies team. The focus of her work at Rolls-Royce has been on the development and validation of new materials for future aerospace applications. She is currently the materials lead for Rolls-Royce hydrogen burning gas turbine engine demonstrator program. And I had the pleasure working, I still have the pleasure working with Louise in a project currently looking at the wear performance of hydrogen barrier coatings when testing high pressure hydrogen. And it's a really pleasure to have her presenting today. Over to you, Louise.
Great, thanks very much. Thanks for the introduction. Can everyone hear me at the back? Yeah, perfect. Oh, that's... Okay, thanks everyone. My name is Louise Gale. I'm a material specialist. I work in the Future Technologies team at Rolls-Royce. So we look at the next generation of technologies for aerospace and power applications with a particular focus on sustainability. So within aerospace, there's a big growth challenge. We expect over the next 20 years, society's demand for aerospace for travel is going to increase by over 4% every year. And so as the aerospace industry, we have a responsibility to ensure that this is a sustainable growth through the development of technologies, to make it sustainable and also start to drive down those emissions with the focus of net zero in 2050. So within Rolls-Royce, we have 3 pillars of our journey towards net zero carbon. It's worth saying up front that there's not one single solution that's going to take us towards net zero. It's going to be a combination of different solutions that really depends on the size of the aircraft, the power and range of the aircraft too. So the first pillar, and probably the most important in the short term, is really just continuing to work on maximising the efficiency of our current fleet. So driving down fuel burn, whether that's through new materials developments, through new designs, new systems, but that has a much quicker impact on the fuel burn right now than some of the longer term technologies. So, and also those improvements will continue to read across to the new technologies and new fuels, assuming we continue to stay with gas turbine architectures. So moving forward, the second pillar is SAF, which stands for Sustainable Aviation Fuel. So typically we fuel all our gas turbines with kerosene, which is fossil fuel derived. So sustainable aviation fuel is in the name. It's from renewable and sustainable sources. So typically either refined from organic or waste substances or synthetically made using carbon captured from CO2 from the atmosphere. So this in theory is a great solution. It's a drop-in solution. We could pretty much put it into our existing engines. For example, Rolls-Royce have shown all of their different engines are currently work with sustainable aviation fuel. However, there's some big challenges here, really. One, the production. If an airline went out and said, I want to run all my aircraft on sustainable aviation fuel, they just simply couldn't get the amount of fuel they require. Currently, it accounts for less than 1% of the global use of aviation fuels. It's also very expensive, so that will kind of have a knock-on effect on prices. And also, we've got to ensure it doesn't compete with food supply if we're taking it from organic matter or waste organic matter like crops. So the longer-term pillar, the third pillar, is really looking at more true net zero carbon, alternatives like electric engines, and also hydrogen, which I'm going to talk about a lot more today. So hydrogen in aerospace. It's been discussed a lot over the last few years. There was a lot of buzz about it, and it's definitely going through a cycle. It's fair to say there's some really significant challenges, both technical, but also economical and political, that really we need to overcome before we will get towards hydrogen aerospace. This is myself quoting, it's not Rolls-Royce, but I think it's probably at least 20, 30 years really off seeing it in service. But we need to start the work now if it's ever going to have an impact. So what sort of role will it play in aerospace? So in terms of, I've already talked a bit about sustainable aviation fuel versus hydrogen. Hydrogen is less of a drop-in solution, but a true net zero solution. Hydrogen also has the potential to be cheaper than sustainable aviation fuel. If sustainable aviation fuel is synthetically made with carbon and hydrogen, you will need hydrogen anyway, so it's just one step back along the process route. It is worth highlighting at the moment that most hydrogen at the moment is produced from fossil fuels, but there is the ability to produce it in a green way, which is electrolyzing water with the use of renewable energies. There's a big question about whether you use hydrogen in a gas or a liquid state. The current consensus is that it would be liquid state, essentially the volumetric efficiency, density. If we had gas, hydrogen on the planes, the tanks would just be too big, they would take up too much of the plane. So we really need to use it in the liquid form, or at least store it in the liquid form of the plane. So that adds a whole new challenge in terms of dealing with the cryogenic aspects, as liquid hydrogen is around 20 Kelvin. Within aerospace, there's two options for the use of hydrogen. You can either put it into traditional gas turbines or look at the use of fuel cells. Some early studies done within the aerospace industry suggest that fuel cells could work for shorter sort of commuter vehicles, but the weight really restricts it. So for short haul or long range aviation, essentially commercial aviation, it's much more likely that gas turbines would be the route forward. In terms of short or long range, in the short term, the aim is to look at engines for short range. This is sort of hops to Europe rather than transatlantic flights to America. That's really around the design of the tanks and ensuring the tanks, there's still room left on the plane once you put the tanks in for the passengers, but potentially redesign of the airframers might open up more opportunities to use it long range in the much longer term. And then there's airports. There's a big challenge in airports around dealing safely with hydrogen. The infrastructure just isn't there. We need to ensure that you can have the hydrogen piped into the airport. It needs to be liquefied, so probably liquefied on site. But you also need to think about challenges like refueling. Typically now when you go and get on a plane, they're refueling the plane as you load, and that's really crucial for people like EasyJet and Ryanair to allow those fast turnarounds. Whereas if you use current safety rules for hydrogen, the exclusion zones would mean that passengers wouldn't be able to get on the plane while you're refueling. So there's a lot of challenges in the airports. So how would this look like on an aerospace gas turbine, and what are the main steps in the engine, and hence the materials challenges we need to tackle? So firstly, off engine, so this is more with the airframers, so Rolls-Royce aren't looking into this so much, but there's a large challenge around tanks, improving the gravimetric efficiency of tanks. Traditionally, tanks for liquid hydrogen would be metallic, but that's quite heavy. There's quite a lot of active research in the area of composites, but hydrogen is very leaky. If there's a small place it can leak out of, it will, cracks, pores. So the sort of sealing and certification of composite tanks is a big area of active research. As we move on to the engine, we're going to have the liquid hydrogen piped onto engine, so it will be quite low pressure. So first we need to bring it up to pressure to allow it to be pumped into the engine to be eventually burnt. That pumping unit has several materials challenges. We have to ensure all the materials are compatible with the cryogenic temperatures, ensuring seals, bearings, and other such functional materials will operate at those sorts of temperatures. Once we've got it up to pressure, we then have to warm the hydrogen up. Because we can't burn liquid hydrogen directly as a liquid, it would be too unstable, so we need to warm it up about ambient. So that's going to involve putting a lot of heat and energy into that hydrogen, so potentially through heat exchangers, some big thermal gradients, and some big sort of challenges in terms of the stress state those heat exchangers might see. And finally, we need to be able to meter So control the flow of hydrogen to give different power through the engine and then burn it. So within Rolls-Royce, we've got an active demonstrator program looking at testing early, trialing fast, to look at whether we have a minimum viable product for hydrogen, to understand, start to tackle those technical challenges and really prove that this can be done and done safely. So back in 2022, we had on the left this engine here. This was run back in 2022. It's called our Lavoisier engine. This is run completely on green hydrogen, so sustainable hydrogen. It was an AE2100 engine. This was really the first step on the journey. We were demonstrating safe fuel handling, so most of the fuel control and metering was done off the engine, and it was piped onto the engine to be burnt and run the engine. But we did really show some key things that we could start the engine, we could ignite the engine safely and then shut it down and control it, which are really key steps in demonstrating the safety of hydrogen. But it was at fairly short timescales and fairly low power. So our main program is the two left engines here. It's actually the same engine, but 2 iterations of it. So it's a PAL 15, so it's a business jet engine, about 15,000 pounds of thrust. So about 2 years ago, we ran our first engine, Engine 0. So modifying an engine from kerosene to hydrogen means actually it's not just the fuel system that changes, but the hydromech system changes and the thermal management systems change. So we tested those first in Engine 0 indoors in Germany. And then the final engine is our gaseous hydrogen engine. So we're doing a gaseous hydrogen engine first and then developing the cryogenic technologies in parallel. This engine would essentially be a traditional gas turbine. You'll have the compressor will be as normal, the turbine will be as normal, but the fuel system will be completely redesigned to work with hydrogen, and the combustor also adapted to work with hydrogen. So this engine would have all of those controls and fuel system on engine, so what it would look like if you were to take it onto a passenger jet. And we plan to take this engine up to full power and really demonstrate the full operation of an engine rather than the sort of low power mode we did in the early tests back in 2022. So in terms of the technical challenges, the talk's about materials, so I'll come on to that in a minute, but just to highlight, there's a lot more than materials here. There's the architecture and cycles. So our gas turbine demonstrator engine very much looks like a traditional gas turbine, but there is potential to redesign the gas turbine more substantially to take advantage of the fuel, take advantage of the cooling of the fuel that you have in liquid hydrogen. You can also use the engine in quite different ways in terms of how you cycle it. Currently, if you go in a plane, you climb hard. That's to burn off the fuel, because the fuel is a large proportion of the weight of the aircraft, whereas with hydrogen, the weight is actually really in the tank rather than the fuel, so you could climb more steadily. So the way you fly with hydrogen may be very different in terms of optimizing and reducing fuel burn as a total. From a combustion perspective, hydrogen doesn't produce CO2, which is the main reason for using it, but we still have to consider emissions like NOx, and also we'll burn to produce a lot of steam, so we have to consider the effect of contrails on the environment and global warming. On safety and certification, that's a big one. We've got to prove this is safe. Currently, if we went to the aviation safety agencies, there's no current framework to certify a hydrogen engine, so we need to work closely with the rest of the aerospace industry and the agencies to really develop that certification and safety protocols to ensure things are safe. There's challenges around thermal management. Normally, we used to our engines being very, very hot, and now we have some very, very cold aspects of it there as well that we need to manage and ensure the heat is in the right places. This could be used to our advantage, but is a big challenge. We also need to ensure we really can control the flow of fuel. So from a materials perspective, the challenges range across the whole engine, across the whole temperature regime. So if you think of the fuel coming into the engine cold, first we have to deal with the cryogenic elements of this. So some materials will have a ductile to brittle transition as you take them low, so we might have substantial ductility loss. We need to understand how these materials are going to deal with thermal cycles, because engines won't stay constantly cold. When you come and land, the engine will turn off and warm back up again. Really, at the moment, there's just a lack of materials database at cryogenic temperatures. So simple properties like coefficient of thermal expansion, modulus, our understandings of those at cold temperatures, we have very little data. There's a little bit of data from the space shuttle work at NASA, but there's a lot more we need to do. And it seems we can't design components. For example, if you're thinking about putting together a pump that's going to be cryogenic temperatures, everything might fit together and move at room temperature, but if you have differential thermal expansions, you take it down and you don't fully understand that, you could have either the whole thing seize or go completely loose depending on how the thermal expansion is different. So we have to really look at measuring these temperatures and materials performance of these sorts of at cryogenic temperatures. There's a real lack of test capabilities and standards. We've been working with different universities and the Royce Institute to try and promote development of further kits in this area. We also need to think about the performance of functional materials like seals and bearings and how they are going to behave at these sorts of temperatures. As we warm up in temperature, we start to get the challenge of hydrogen charging and embrittlement. This is when hydrogen diffuses into a metallic system and it will sit interstitially within the microstructure and affects the plasticity mechanisms within the material and can cause significant reductions in performance. So this is seen as a knockdown in ductility, an acceleration of crack propagation, a reduction in fatigue life. So it has some really big effects. It varies on different metallic systems to varying extents, it seems, but it's really something we need to understand how that hydrogen embrittlement effect is seen. It's particularly bad for nickel and titanium alloys, which are very extensively used in gas turbines. So we really need to look at our alloy selection and how we life components and take into account hydrogen embrittlement when lifing aerospace components. Some of the challenges, hydrogen embrittlement I think was first observed over 100 years ago, so it's not a new phenomenon, but it's fair to say there's some debate in literature about exactly the mechanisms at the atomic level of what is happening. And also the research at the moment really focuses at room temperature with simple screening tests, whereas we need to be able to life an engine, we need lifing tests like fatigue and creep to be really able to say how well our components are going to last. And also there's a real lack of data at the extremes of temperature. Our engine will probably see 20 to 1,000 Kelvin, whereas the majority of test data and literature is at room temperature. Again, there's a real lack of test capability within the university network and commercial test houses. So we can't just go and do these tests to fill the gaps. And also we need the standards to be able to show we have high quality data to prove to a high level of confidence that our engines are safe to fly. And we also need to think about the effects of leaks and transients. So we can design our fuel system to use materials that are generally less susceptible to hydrogen embrittlement, but we can't completely remove titanium and nickel from our engines. So we need to understand if a pipe starts to leak onto a titanium fan case, how is that going to affect its performance? There's also opportunities in the area through potentially the development of hydrogen barrier coatings to slow the diffusion of hydrogen into metallic components, and also maybe around alloy design. As you go up in temperature, you have hot hydrogen attack, which is when the hydrogen diffuses into the material but actually reacts, so forms hydrides or forms methane if it reacts with carbides. We generally think that's not such an issue for our engines just due to the materials we use, but that's something that needs to be considered. And then once we get up to the highest temperatures, so once you've burnt the hydrogen and you're in the turbine, great, the hydrogen embrittlement risk has gone away, but now you have probably 3 times the amount of steam going down your combustor in your turbine, and we really need to understand how that's going to accelerate the corrosion of both the metals and the coatings in our turbines, how that's going to affect the life of those components. So some of you might be thinking, wait a second, other people use hydrogen in other industries. This is not a completely new thing. Aerospace is not the first person to use hydrogen. So this slide just really focuses on what some of the challenges are that are a bit more unique to aerospace that haven't been so well addressed in other industries. So we just generally have a wider range of pressure and temperature requirements. A lot of industries are much more static. They're sort of a static, single pressure, single temperature, and the component will just run. Whereas we see a much wider range, both hot and cold, and it will then cycle. So we need to understand how that imposed temperature and pressure cycles that we'll see in the engine will affect component integrity from a hydrogen embrittlement perspective. We also need to understand how those thermal cycles are going to affect things like sealing as well in the engine, because it's really key from a safety perspective to ensure the hydrogen doesn't leak. I already mentioned a bit about different material systems. We use a wide range of material systems in our engines, so we've got to re-qualify them all for use in hydrogen or reduce the number of materials we use, which is going to be very expensive when there's a sort of real lack of hydrogen test kit, and just due to the health and safety requirements, where there is kit available, it can be quite expensive. So currently, if you looked at how the design codes for, say, oil and gas and how they deal with hydrogen, the piping design codes from ASME will just currently say, drop the stress, because hydrogen embrittlement, if you haven't got the stress, it doesn't occur. So they say, drop the stress to the point where you get to infinite life, which is great. So you just reduce the increase the cross-sectional area, drop the stress, and the embrittlement risk decreases significantly. We can't do that in aerospace. If we did that, everything would get really heavy, and we're never going to get the plane off the ground. So we need to have a better understanding of hydrogen embrittlement and how far we can push components before we get a risk of component failure for hydrogen embrittlement. And it's worth saying that NASA, a lot of the literature in terms of past work with liquid hydrogen is from NASA, from the space shuttle work, and some really good work there. However, the space shuttle the sort of pumps and the liquid hydrogen components tend to run for a few hours, whereas from an aerospace gas turbine, we typically run 10 to 20,000 hours between overhaul and inspection. So we need to make the liquid hydrogen components run significantly longer than what NASA did. So, it's 3 orders of magnitude longer use. So NASA's done some really good early work, but they didn't look at that long-term use. So in terms of how we start to put together a test pyramid in terms of a testing framework and the different sorts of testing we do, this is not just for hydrogen, it's for anything within aerospace. There's different levels of tests. There's the simple, cheap ones up all the way to the very expensive, doing a whole engine test. And these have different benefits. As we go up, things get more expensive, but also as we go up the pyramid, the risk reduces more significantly. So we tend to start in the early, lower TRL levels with simple screening tests, then move to lifing tests, then we start to move towards component tests, and then finally engine tests. So SSRT stands for slow strain rate tensile. It's the industry standard test to test for hydrogen embrittlement. It's relatively simple and quick, and there are actually test standards available. However, and this is what's primarily reported in literature, so it is a really good, there's a really good database out there, but it doesn't really represent true hydrogen service, and it can't be used for life components. It can only be used to say this alloy is better or worse than this other alloy. It doesn't say whether either alloy will last for 1,000 hours in service. So we really started to now move on to lifing tests, so fatigue and creep, because they're much more representative of engine service, but they're much more complex, they're much longer, and hence more expensive, and there's much more limited expertise and standards available in this area in terms of how to do this in hydrogen and get fully representative results. So hydrogen's quite a challenge to test. Traditionally, you can introduce hydrogen into a material in 2 ways. You can set up an electrochemical cell, or you can put it in a high-pressure hydrogen. Electrochemical cell, from a health and safety perspective, is a lot easier to set up, and it's what's often done in literature. However, it's limited to room temperature, and it's not really fully representative of gaseous charging. There's not a numerical relationship to say if you put it in this electrochemical cell, it's equivalent to 50 bar of hydrogen gas. So within our test program, we've really focused on gaseous charging, that adds much more testing complexities. So the tricky thing about hydrogen, it likes to get into everything, but also likes to go away very quickly. Some testing will look at putting a test piece in a autoclave, charging it at high pressures and temperatures. So you've got nice hydrogen charged sample, and then taking out and testing it in air. That's much more simple from a health and safety perspective and a testing perspective. However, hydrogen will like to outgas just as quickly as it's gone in. So you risk through your tests, especially longer tests like fatigue and creep tests, the hydrogen leaving the sample as you go. So you can test it in a high pressure chamber in situ, which is the sort of gold standard. But this is challenging because as you put the pull rods to apply the load to the specimen, they have to leave the chamber at some point, so there's a real sealing challenge that particularly becomes challenging as you get hot. There's also methodologies using, which is the far right, which is using hollow specimens where you throw the hydrogen down the center of the specimen. It's much smaller volumes of hydrogen, so much easier from a health and safety perspective. So hydrogen embrittlement, it's a real challenge, not just because of the effect, but also because how variable it can be and how many factors affect it. So this table on the left is from NASA. It's of Inconel 718. On the right, the number on the right of the table is the hydrogen embrittlement index. So 1 means it's not embrittling. It's looking at the knockdown in notch tensile strength. 0.6 means a 40% reduction in notch tensile strength. And you can see for just different heat treatments of Inconel 718 and different forms, you can go from sort of almost just a 10% knockdown to at least a 50% knockdown. So there's a real variability in performance. And often if you go in literature, you don't get this amount of pedigree in terms of what exactly has been tested. There's a real variable performance. The bottom image shows 316L, which is an austenitic stainless steel. It has quite a wide nickel range. And again, you can see if you're at the top end of the nickel range, you have no embrittlement, whereas if you're at the bottom end of the spec range of nickel, you can have up to a 50% knockdown in, I think this is reduction of area. So there's real challenges around just how sensitive the material can be to hydrogen embrittlement, even within a given spec. So in terms of surfaces, this is a surface session, so moving on to surfaces. A lot of people look at the bulk diffusion, the diffusion of hydrogen within the bulk, but the surfaces are really important in terms of how this hydrogen is absorbing into the alloy and can have a real effect. So there's a few different factors. I've pulled some nice images from literature here, just showing the top left shows some looking at surface roughness, some nice work from Cranfield that I've been doing with Cranfield, showing that as you increase surface roughness, the uptake of hydrogen increases significantly. The one on the right looks at shot peening. This shows with shot peening, you get a significant drop in hydrogen uptake. And the bottom images show the permeation into X80 steel with and without oxide. Essentially, once you start to put oxide films on, an oxide film on a component on X80, it really drops the hydrogen uptake. Surface condition is very rarely reported in papers. So I was saying before about specimen pedigree and what specs. People might say what spec the material is and what heat treatment. It's very rare for them to have looked in detail and recorded in detail what's the surface roughness, is there an oxide, how thick the oxide is. So surfaces are really important, and understanding their effect on hydrogen permeation and uptake is going to be really key, because hydrogen embrittlement isn't just a switch. You need a critical level of hydrogen to diffuse into a metallic system before it really starts to show significant hydrogen embrittlement. So we need to understand these surfaces and how they're affecting hydrogen uptake to really be able to quantify levels of hydrogen embrittlement. It's also worth saying hydrogen has a significant effect on tribology as well. So within all the turbo machinery engines, like for valves, pumps, seals, we really need to be aware of the effect of tribology. So some nice figures from industry, from some literature here, showing the significant effects. The top and the bottom left images show the significant effects hydrogen can have on the coefficient of friction. And also the images on the right show the significant effects hydrogen can have on wear rate, so it can increase wear rate and also increase, this shows some increase in wear rate and hardness for some pipeline steels. So we really also need to start looking, and this is an area which is much less explored in terms of, if you look at the amount of literature on hydrogen embrittlement, there's a lot. The amount of literature on hydrogen effects on tribology is fairly limited. So it's why we've really started to actively work with Leeds to look much more into this area. So just to wrap up, some nice pictures. I think I've talked through the first two. The picture on the left is our first run in 2022, the first modern aero engine on hydrogen. The picture in the middle is when we ran all the other, our sort of engine zero, looking at all the non-hydrogen systems. And on the right, we've got some images. At the top right is some images of hydrogen combustion testing in Germany, burning hydrogen up to full engine representative pressures. And the bottom right image is some of our early testing of some liquid hydrogen pumps that were designed in collaboration with the MTC. So it's a bit of a whistle-stop tour, but thank you very much for listening. You've got any questions?
Thank you, Louise. Any questions? Yes, one there, and then we'll start with that.
Hello, my name is Sergey. I am from Zerevia, and we are focused on the hydrogen electric powertrains. And we just finished our composite tank for the liquid hydrogen.
Yeah.
And I guess our challenges are quite the same. So my question is, what do you think is the top 3 of challenges around the mass and the weight? Because I guess that's the main thing for the all aircrafts. And what is your point of view on that? Thank you.
Sorry, challenges around?
Around the weight.
The weight. I suppose the challenge really is that within our aircraft, with our engines, we use a lot of high-strength nickel alloys, and they're highly susceptible to hydrogen enrichment. So it tends to if you look in literature, the higher the strength of the nickel alloy, the more susceptible to hydrogen enrichment. So it's exactly the reverse of what you want to do if you want to drive up stresses and drive down cross-sectional areas. So it's really probably trying to find the sweet spot in the nickel alloys as we move into combustion systems where the traditional austenitic steels, which are good in hydrogen, start to just run out of temperature capability. So I think, yeah, the use of the nickel alloys are probably the biggest challenge in the hot end of our engines in terms of weight and hydrogen.
Okay, there was another question here from Rick, please.
I mean, part of the driver for nickel alloys and single crystal turbine blades and coatings is to drive up temperature.
Yes.
Because you get more efficiency. But if you're using hydrogen, do you really need to worry about efficiency so much? Because the emissions are...
Well, I suppose we still want to look at minimising fuel burn. It's still there are still concerns around emissions with NOx, so nitrous oxide, and also contrails, which is the steam out the back of the engine. So we still need to reduce emissions. And also one of the challenges with aerospace is fitting the tanks on the aircraft. So if we are less efficient in the engine, we need bigger tanks and there's less space for passengers. So I see what you mean, but there are still emissions we're concerned with, and there is the constraint on tank size and current aircrafts that will mean that we're still looking to continue to increase the efficiency of an engine as a whole.
I'm just thinking philosophically, are you completely wedded to nickel-based superalloys? Whereas actually maybe something else might.
And there's also options here around, normally we really struggle to cool the hottest bits of our engine, whereas if we have some really cold, thermal management's going to be a big one. If we can transfer heat around to take some of the heat from the hot end of the engine to do the warming up of the fuel in the first place, there might be an element where we can bring down the temperature of our turbine blades and then maybe look to other alloys. But at the moment, that's not yet a consideration. But I think there's a lot of work looking at architectures and how it might fundamentally affect what a gas turbine looks like and what it's made of. So yeah, it could change.
Okay, any other question? Okay, just one question, quick from me, Louise. You mentioned the lack of testing capabilities. And for a company like Rolls-Royce, I guess you can manage that. But how important is that for supply chain industries? Companies that manufacture seals, bearings, and other components which are used for hydrogen transport and rather than the end use.
Yeah, I think it's needed across the full chain of the full manufacturing chain will need these capabilities, and we're looking to try and work with other industries because it's pre-competitive. We all need this kit, so we're really looking at other opportunities to work with other industrials to try and develop the standards and the kit as well. And we've worked a lot with Royce in terms of trying to promote the roadmaps for what's needed from a hydrogen test capability perspective.
Great. Well, thank you very much, Louise, for
thanks.
a very nice, interesting presentation. Okay, our second presentation is from Dr. Robert Menzel from School of Chemistry here at the University of Leeds. Robert is associate professor in the School of Chemistry. He obtained his PhD in carbon nanomaterials chemistry at Imperial College, and after working as a postdoc at Imperial and UCL and as a scientific consultant at BioNano Consulting, he joined in 2015 University of Leeds as a university academic fellow. His research is focused on the assembly of inorganic nanoparticles into multifunctional porous materials for sustainability-related applications such as water treatment, CO2 capture, and catalysis. His research combines fundamental materials research with a strong drive to support the development of commercial nanomaterial technologies. Over to you, Robert.
Thank you very much. Thank you for the opportunity to speak here. So I'll be talking about on quite a different aspect on surfaces. So it's very complementary, very different perspective on surfaces I'll present here. So I'll talk about the engineering of graphene surfaces for catalytic transformations. And the surfaces in question here are actually within another type of porous material. So in the first session here, we had really nice talks on various porous materials. Here, another one, graphene foams. So sponge-like assemblies, 3D assemblies, centimeter scale. We are producing these, made in our case via hydrothermal self-assembly. And these materials are highly porous. So if I mean highly porous, really quite the opposite of what we just heard. So we have an extremely porous material here, larger than 90% porosity void space in them. And these have really quite large pores. So just to stress that in comparison, for example, to Andrea's talk, where we talked about nanometer type pores, here we talk about pores on the mesoscale, micrometer-sized pores. And we have now these graphene frameworks, 3D frameworks, and the thing I'll talk about in this talk here is their use to support catalytically active metals, usually in form of a nanoparticle within this structure. And because we have very large pores now, and a high surface area material, all these catalytic units on the surface are now accessible. So what the application we want to look at the end is really flowing reagents through these pores and utilize the catalytic activity of these nanoparticles. So the surfaces are graphitic surfaces I'm talking about here within the pores, and the functionality is catalytic functionality. So we do these hybrid metal foam structures with quite a range of metals. These have very large application fields. In the literature, it's quite a large area of interest, very much driven by electrocatalysis and batteries, in fact. We heard a bit about flexible materials as well today already. We will look here at an area which is a bit understudied in this area. So we will use these materials for chemical transformations in flow, particularly. So while this is a surface session, if you work with these type of foams, at least one slide on showing that a big driver of working with these kind of macroscopic assemblies is that you can structure them quite nicely on the mesoscale, so on the micrometer scale. So these are some examples from our group here in Leeds. We're using different templating approaches. So you really have a big range of this, ice templating, emulsion templating, or we're also using templating around microfluidic droplets. And we can create all these different architectures, different morphologies within the pore structure and different sizes, from aligned channels to micro cages, for example, for delivery applications, or these kind of X-ray structures where every cell is exactly the same size as the other. But for this work, I'll stick with these materials here. We have microchannels through the foam on the micrometer scale. You can imagine this is where your reagents are going to flow through then and be converted into the product you want. So as I said, we want now to look at the surface of these pores, these graphitic surfaces. And I thought I'll give at least a brief overview what kind of surfaces we look at. So for these foams, we are talking about, we typically talk about something that's called in the field reduced graphene oxide, RGO. This is somewhere in between the two graphene derivatives were mentioned in Cecilia's talk. So it's something in between a perfect graphitic sheet, which is completely aromatic, versus the original building block for this graphene oxide, which has a lot of oxygen in there and has quite a lot of different properties to graphene. So during our processing, normally we end up with surfaces which are constituted of reduced graphene oxide. And these are characterized by nice large graphitic domains, so where the surface is really graphitic, and a lot of pi-pi interactions, for example, can happen. But in this material still you have a lot of defects which are saturated with oxygen-containing groups. So there's maybe 3 to up to 5% of oxygen typically in these materials. And they're present in your classical organic functional groups, quinone, lactones, for example, very typically found there. And context here of a materials conference, you used to do things like XPS, very early on really titrations to figure out what kind of groups are on there. And nowadays, seeing is believing. You have these capabilities now to really atomically resolve the structure of these defects and can really confirm these kind of types of oxygen groups present at the surface. So then we want to bring in metal species. Don't quite have the time to go through all of these, so you can do this in different ex situ or in situ ways. We have settled on a way where we do nanoparticle synthesis in situ. So what we do is we start with molecular precursors that contain the metal. The molecular units can diffuse much easier into these 3D objects. So we're talking about centimeter scale type of porous objects. So the mass transfer into these is not easy. It makes it much easier if you work with molecular precursors, and then we deposit them onto the pore surfaces and decompose them thermally. That's what we do into our nanoparticles. And specifically, the process we've developed for aerogels and foams, so I'll use aerogels and foams here interchangeably, is depicted here. So we start with a foam that we have pre-structured, let's say, for example, in these aligned channels. And then we use these type of precursor compounds. You can see these are quite nice and flat, have a certain aromaticity to them. They have an affinity, so they diffuse quite readily into your structure, and then they have an affinity to the graphitic surface they deposit there. And you can actually decorate and load these precursors very nicely and uniformly throughout the whole volume of your porous structure. And then we flash heat these compounds. The ligand systems here fly off. You free up the metal, and during the heating stage, these metal species can coalesce into nanoparticles. That's a general process we follow, and that works really well. So you can choose the precursor and then have access to different types of really nice, fine nanoparticles, copper, platinum, for example, just a few examples. You can also access, for example, metal oxides through that. And for a 3D object, which is really a bit different to a flat 2D surface, you really need to check that you did that decoration really throughout. And this combination of precursor loading and fast precursor decomposition really allows us to functionalize the whole object throughout with great 3D uniformity, really small nanoparticles nicely distributed everywhere in that porous object. Key step here is something we do a lot here in my group is the heating stage, which we do via flash joule heating. Nice complementary technique to the microwave heating, for example, Andrea mentioned. So here, what we do is we have a porous object now, which is in contrast to most porous materials, a monolithic, so really centimeter scale type of object, and electrically conducting. So you can quite easily connect it to electrical current and really send through quite a lot of current through there, but only very briefly, and that gets our framework really hot very quickly. So we can control this via power input, and we reach really high temperatures up to 3,000 kelvins very easily. So we do this under nitrogen in a box from B&Q. We don't need a glove box. So it's quite a robust process, and you can control it quite nicely. And the important thing is not only that we reach really high temperatures quite easily, but also that we do that very, very quickly. So typically for most of the work we are doing, we're kind of going to 2,000 Kelvin, and you reach this really in just a few seconds. And this is really interesting for this decoration, for example, of these frameworks with nanoparticles, so for the second heating stage, because you can really access very quickly high temperature processes, which would be really difficult to do otherwise. And you can do this by this shock heating, if you like, flash heating. You do this very briefly, so you prevent the active metal species to migrate too much across the surface and form too large particles. And in fact, you can extend this to really control particle size via the heating duration. So here an example where you can reduce the particle size quite easily at a Joule heating duration of 10 seconds versus 1 second. So that also highlights that if I mean short, I really mean short heating. The other nice side effect, nice extra bonus if you do this, is that the graphitic surface here itself graphitizes quite easily, so we can really quite readily graphitize the framework, make it a bit stronger, make it more graphitic, more electrically conducting, for example, more uniform in its surface chemistry, and we can go to really nice high graphitization degrees because the temperatures are so high. But importantly, you can also do this actually at quite low energy consumption because you dump a lot of energy in there, but only very briefly, so the energy consumption for this is actually quite low. So this works really well for lots and lots of things. But if I come back to our initial example of copper supported on the surfaces of these forms, then we actually do see that it works, but because these are particles which are capping agent free, and copper has quite a high cohesion energy as a metal, it does form, even at these short durations, quite big lumps, unfortunately. So here a picture on our RGO, where we've chosen something particularly chunky particles that are formed. So we needed to think about a strategy, how can we really get to much finer particle sizes? And what you can do is you can really use the knowledge in the literature on doping graphene surfaces with heteroatoms. Here, example of nitrogen-doped graphene RGO, where you introduce these pyridinic and pyrrolic nitrogens into the lattice. And if you do exactly the same process as you did before, precursor loading, then flash Joule heating, you get a much finer particle size distribution, a much smaller particles and nicely distributed. And if you look at the XPS of this material, you can see why that is. So here in the XPS, we have new peaks that we assign to copper-nitrogen interactions. So these nitrogen sites here, for example, act as anchor points. So they influence the nucleation of these nanoparticles and also restrain the growth of these nanoparticles. So you really access quite easily smaller particle sizes by a simple process. So the doping of these materials can be done in the foam synthesis quite easily by adding doping agents. Just a brief word also that you can do more sophisticated things with the metal itself using that methodology. So you don't need to work with one precursor, you can use a mixture of precursor, and because the deposition process is very effective in depositing the precursors very uniformly throughout, you can actually then use the flash Joule heating and exploit, in fact, not only the fast heating, but also the fast cooling of graphene. Graphene is a very good thermal conductor, so it dissipates energy very quickly once the electricity is switched off. And the fast cooling suppresses phase segregation in these nanoparticles. Here, really nice work by Sean Collins, actually, who's now at Imperial, at SuperStem, which really shows that excellent mixing in individual particles of, here, 5 particles, so high entropy alloys. So what is that good for? Just 2 brief examples. So I said we're utilizing this for catalytic applications. So these are catalysts where we flow our reagents through and really want to use the whole internal surface here. Here an example for gas phase reaction where we degraded benzene, environmental pollutant in the gas phase, using an alloy particle, platinum palladium, on these type of foams. And these are quite competitive in their catalytic performance, competitive to these industrial catalysts. But what I think is really striking here is 2 features of the system. So the one is that we can run these gas phase reactions at very high throughputs, really high space velocities. So I think one of the highest reported for this type of reaction. And we can run it for a very long time. So this is a 100-hour experiment. So this, we believe, is due to the very effective alloying done by the Joule heating. You can see that these alloys have excellent on-stream performance and stability compared to the industrial catalysts here, which degrade under these conditions very rapidly. And then we also have integrated this into a liquid phase reaction system. So here is our foam. You might just see the microchannels here. The channels are aligned like this. So your reagents flows in here and the products come out here. This has been quite a challenge, needed a lot of optimization work. But it is possible now for us to put these type of materials into flow and use basically these materials now as flow-through catalyst for classical organic reactions. So this is a transfer hydrogenation, important for biomass transformations, for example. And you can now exploit all the advantages of continuous flow chemistry Andrea outlined to us earlier really nicely. So here just an example. We can run this also for 100 hours. We can suppress extremely effectively side product formation, which you don't want if you integrate this into flow. But from a materials perspective, it's also quite interesting because we can now use this for testing the materials we do in terms of catalytic performance. So here an example of another alloy system, ruthenium platinum system, which we compare its performance here. This is the yield of this reaction here over time. And we can see that the performance here catalytically is really remarkably higher if you alloy these two metals. So everything else is the same. The only thing is that these two metals are now there in an alloy structure. And now, of course, it's really worthwhile kind of going to our excellent Bragg facilities, for example, here, or even to Superstem, and really look at what's going on in this material. Why is the performance so much better? And it will come in extremely handy if we go now and go into future directions, exploiting, for example, trying to control function and formation of these particles on these surfaces even better. So really what we want to do now is to see if we can create really defined few atom clusters. They are very hard to see by standard characterization methods. So if you can test them first, kind of see how the performance is, and then go and characterize them with excellent characterization facilities, then makes the whole research much easier. So one last word then here, how we go forward. So something we started now in thinking about how to control nanoparticle formation even further. So we have now a lot of tools, so a lot of screws we can turn to potentially achieve nice single atomic sites or maybe a few atom clusters. So you can work with the process conditions, you can work with different precursor compounds, different metals, and different defects, of course, as well in the structure. And of course, to experimentally screen all of this is a daunting task. So led here by my colleague, Ord Monroe in chemistry, we are starting to look into theoretical predictions of the formation of these particles and the interaction of precursor compounds and metal species with these graphitic surfaces. I don't think I have the time to go through the method itself, but please come and talk to us about this. But what we can use it for is really, we can really simulate now with reasonable accuracy, relatively fast, quite large chunks of graphene. So it's maybe 3 to 4 nanometer sized graphene flake here with these compounds. This is the copper agar I had in one of the earlier slides. We can, for example, see that locates quite nicely here in the center away from the edges. We can see we can dump a lot of energy into this system as you do in the flash Joule heating. And you can see, for example, that radical mechanisms here are involved in that high temperature process. And the real power, I think, lies that we can now really leverage the experimental data of high atomic resolution imaging of these defect sites. So really confirmed defects within the structure. We can build models of these, and then we can look at the precursor adsorption chemistry. So for example, if you bring in the defects, you can see the interaction now is with the carbonyl group here, not with the basal plane any longer. We can pull out a lot of interesting, important parameters like coordination chemistries. Where does the charge sit? Are there charge transfer interactions? And we, again, can also look at a snapshot of a high temperature process. Where under these high temperature processes does the metal go? So it seems to wander away, for example, here from the defect. So it would be interesting to see what happens if we build in a nitrogen dope defect, for example, in here, and gain better construct, screen a lot of conditions in silico before we then go and experimentally screen them. So that brings me to the end. I'll probably leave that at the end for our outlook. I want to make sure to thank everybody involved in this. So lots of people involved, the whole team here in the group in Leeds, and of course all the colleagues at Leeds and internationally we worked with. And I'll leave you with this outlook at the end. So as I said, we want to go now towards single atomic sites, small atomic clusters. And one thing I took out for time reasons, but it's also quite interesting, is even if you keep the surface chemistry the same, we see that functionality of these graphitic surfaces can also be controlled by surface topology. So that's another topic for another talk. But that's also something we want to kind of figure out how that works. Thank you very much.
Thank you, Robert. Yeah, one quick question.
So your last bullet gets to a point I wanted to ask you about. Some years ago, maybe 10 years ago now, researchers working on making nanoparticle catalysts showed that if they grew them on certain substrates, it doesn't matter what it is, because of the epitaxial relationship, it made the particles with certain facets, and it also stabilized them against coarsening, which is a big problem in nanoparticle catalysts.
Yes.
So the relationship between the substrate and the particle is key. Here, you've chosen graphene for a number of reasons associated with the topology of the material and sort of a mesoscale, length scale, and the ability to define nucleation sites, but not as a way of controlling the catalyst particle itself in terms of what sites it displays or its stability. And the last bullet kind of gets to this, so can you just say a couple words about that?
Yeah, so it's basically the direction we want to go into. So it's extremely heterogeneous material, as I tried to convey in one of these slides with the surface chemistry of a graphene, reduced graphene oxide, which it normally is. It's very difficult to control. So you need, of course, to advance the control over the defect sites at the same time. So it's quite difficult to get exactly the defect site you want. And that will take a lot of effort. So that's why I mentioned the modeling at the end. So it would be quite nice to kind of figure out which defect we need in the first place to put then the effort in to really produce lactones, for example, or things like that. And then we hope to get exactly that control you mentioned, that you can control facets, you can control particle size, get that epitaxial relationship, for example. Thank you.
Okay, in the interest of time, I suggest we move on to the next presentation. Robert is around, so please catch up with him during lunch or in the afternoon session. Thank you very much, Robert. Okay, our final presentation for this session is from Dr. Farnaz Motamen Salehi from the School of Mechanical Engineering. Farnaz is a lecturer, appointed lecturer in the School of Mechanical Engineering in 2023. Her research is focused on tribology, biotribology, and bioturbocorrosion, involving material testing, characterization, analysis. And the presentation today will be relevant to cubes. Yeah, this is surface micropitting.
Thank you, Ardian. Good afternoon, everyone. Thanks for being here. I know we are overrunning the session. Don't lose interest. I try my best to keep it short. Today, I will be talking about the micro-pitting of functional surfaces and how lubricant additives can affect micro-pitting. This work has been done in Leeds Institution of Functional Surfaces in collaboration with Cargill. Thanks to all the people involved in this work, especially our research fellow, Dr. Aladdin Omar. What is exactly micro-pitting? Because the motivation from this work comes from very practical challenge in industry. The micro-pitting is an early stage surface fatigue happening in rolling, sliding components such as gears and bearings. It starts with a very small micro-pits on the surface due to repeated stress on the surface, and then if it carries on, it might lead to macro-pits and eventually crack and failure in the system, which can be very costly. There are different factors influences micropeating, such as contact and operating conditions, lubricants formulation, and additives, which kind of makes it hard to predict whether micropeating will happen or not. Why should we care about micropeating? Because obviously, if micropeating happens in the surface, it will reduce efficiency, it will increase vibration and noise, it will lead to early replacement of components, and if it leads to the failure, obviously it costs a lot of money for different industries, from wind turbine gearbox, from industrial gearboxes, or automotive drivetrain. So although it's a microscopic damage, it can lead to macroscopic cost. So the aim of this study was to understand how lubricant additives affect micropeating damage, specifically focusing on sulfur-containing and ester-containing additives. So we focused on different oils, PA oil, sulfur-free for a reference, and PA oil containing sulfur, and two different esters which are provided by the company Cargill. So in all this oil, we kept the sulfur level quite high, and we kept the viscosity of this oil almost similar to kind of neglect the effect of viscosity and just focus on the additives here. In terms of the experiment, we used micropeating test rig, which simulates exactly the same condition we will have. Rolling and sliding contacts. This is the test chamber, and this is the close-up images of the test chamber. We have 3 rings here and a roller in the middle, which are in contact, and then we have the lubricants in this chamber. So we ran the test for 100 million cycles, equivalent to 100 hours, and then stopped the test at different points to take the roller out and look at the rollers to see how micropeating has been generated over the time. And the test conditions have been designed in a way to make sure we can generate micropeating within the time frame that we had. So the result shows that, interestingly, the friction coefficient remains largely unchanged across all oil samples. But the peak-to-peak acceleration, which we use as a proxy to kind of track the damage evolution, it's clearly different between the sample. For the sulfur-containing PaO, we can see the peak-to-peak acceleration, it increases significantly. And when we have the ester in the oil, it kind of stabilizes the situation. This is in agreement with what we saw on the microscope images. So as I mentioned, we stopped the test at different points, but just I have presented some of the results here. But you can clearly see the difference between the micropits on the surface. When we have the sulfur in the PaO, we have significant increase in the micropits on the surface, and when we have the sulfur-free, we still have the micropits, but it seems that when we have the ester, the micropits are quite less. So we can say that addition of ester significantly reduced the damage, but we want to see what happens on the surface further, what happens on the film forms on the surface. So we have done some Raman analysis, and with the Raman, we can see that sulfur-containing PaO forms iron oxide and amorphous carbon, and we have seen the iron oxide on the oil-containing esters, but with a much smaller signal. So that shows that ester addition to the oil can reduce the iron oxide formation. In order to confirm that, we did the TM FIB for some of the sample, which we can clearly see that when we have the PaO containing sulfur, we have a thick layer of oxide here. However, when we have the ester, it's a very, very thin layer. So again, it confirms that addition of ester reduces oxide growth and resulting in a much thinner surface film, and this is in agreement with what we saw in terms of growth of micropitting on the surface. And we did a very few tests on hydrogen permeation, just because this is linked with the oxide formed on the surface. We wanted to see how it behaves, so we used an electrochemical cell to measure hydrogen uptake during the sliding contact. We ran the test for 2 hours, and then you can clearly see that when we have the ester-containing oil, it significantly reduces hydrogen uptake during the sliding. So all of this, it brings us to the conclusion that, first of all, micropitting is not only a mechanical challenge, it's a chemically driven phenomenon as well. And when we have the ester, it reduces oxidation, and we have lower hydrogen uptake and kind of protect the surfaces to have less crack growth, which leads to the micropitting and eventually macropits and failure. So the conclusion here is lubricant chemistry should be treated as a design parameter, not a lubricant choice. As we can clearly see here, we're adding ester as an additive. It can reduce micropitting significantly. Thank you so much for the attention. I tried to keep it very short.
Thank you very much, Farnaz. Again, a quick question before we go for lunch, if there is any. Yes, please.
Thank you. That was an interesting talk. What is the ester? Or did I miss it? What was the structure of the ester?
It's an additive that we normally use, and it's a chemical.
What's the structure? What is the chemical? Is it a long chain ester, or is it?
It's alcohol. And
I think this was one of that part which didn't disclose completely what is the nature of the ester.
It's provided by the company, and we can't probably disclose.
Yeah. Well, the key point was the kind of the OH groups and kind of film forming properties of the esters, which kind of made the difference in the results. Okay, well, thank you very much, Farnaz, for the presentation. Thank you all, and I'll pass over to Claire for a final comment. Thank you for enjoy your lunch.
Thank you. Just to say, we are aware we're running over, so lunch is going to be extended by 15 minutes, so we need to be back in here for 2:15. Follow the team to the refectory for lunch if you don't know where you're going. See you later.
Right, welcome to our final session today of the Bragg Symposium. We've got a new thing this year, which is called the Bragg PhD Spotlight Talk. It's going to be given by Oliver Ayre from School of Chemistry. And what we decided, we have a PhD colloquium which happens June, July time each year. For any PhD students in the audience, put that in your diary, you should be coming to it. And what we decided this year is take the winner of the Best Talk Prize from the PhD colloquium and ask them whether they would give a talk at the annual Bragg Exchange. So Oliver won the talk last year with a presentation on a new mechanism for pyroelectrolyte-mediated biomorph growth. And today, in 10 minutes, and no more than 10 minutes, he's going to talk about a new mechanism of biomorph formation. So Oliver, over to you.
Okay, so today I'm going to talk about biomorphs, which are synthetic minerals, but despite their simplicity in the way that you form them, they're able to form these really complex hierarchical shapes. So why do we care about hierarchy? Well, biominerals are usually hierarchical, and they do this for good reason. So hierarchy is features at one length scale that organize to define structure at the next. And a really nice example of this is enamel. So this is the strongest mineral found in our body, and it kind of encapsulates our tooth. And it's formed of hydroxyapatite crystals, which on their own are not particularly special or interesting. But when you form them in this way, with this interwoven structure made from these rods, which themselves are made from hydroxyapatite nanowires, you impart to the material new properties which the crystal on its own did not have. So obviously this is something we would like to be able to do synthetically, but these biological systems are very complex. They usually involve templating, controlled delivery, as well as organic additives. So I wanted to simplify this and really understand the mechanism of how hierarchy and complexity can emerge even in very simple systems. So here we have the biomorph system. So we call them biomorphs because they're synthetic crystals that appear biological. And we say this because despite being crystals, they're characterized by their kind of curved morphologies and non-faceted shapes. So here I'm showing some kind of interesting like gnome house looking crystals, these bundles of wires, and even within helices there's a huge amount of variety in the morphology. And the beauty is we form them from this really simple system. So all I have to do is mix strontium, sulfate, and this polyelectrolyte, so PAA. And it produces this diversity and complexity in the morphologies. So here I just want to demonstrate that indeed, despite the simplicity, they are able to generate hierarchy. So we have this macro-sized cone, which appears to be made from these smaller sized cones, which when you zoom into those, appear to be made from nanoparticles. And this is a really interesting example of hierarchy that is called self-similarity. So if I zoom into these crystals, I see cones, and if I zoom out, I also see cones. So they're effectively scale invariant. But first I want to talk you through how we think biomorphs form more generally, so describing all of those morphologies that we saw earlier. And I'll revisit these self-similar cones later on. So generally, people think because of those nanoparticles that we observed here, people have come up with theories based off that alone, sort of. So they believe that nanoparticles aggregate in solution and add to the tip of your growing biomorph. And that seems reasonable because in the structures, we do see that they appear to be made from nanoparticles. But this kind of ex situ characterization is quite limited when you want to understand mechanistically how crystals form. So I watched these biomorphs grow on an optical microscope time-lapse, and I saw something really quite surprising. So here we have a biomorph that is growing off a glass bead, so that's a substrate that we like, that the biomorphs like to grow off. And as time goes on, I saw something really interesting here, that as time goes on, the shape of the crystal at the tip of the biomorph does not change. So the biomorph is growing longer, But the shape is not changing. So if particles were adding to the tip of this crystal, you'd expect the shape to change with time and length. So this kind of implies, well, is the biomorph just growing off the glass bead? But when you draw that out schematically, something doesn't really make sense. So we have this solid-solid interface here where the growth front is along here. And so how would ions actually diffuse in to feed the growth of this biomorph? So if instead you alter that slightly and you add some thin layer below the crystal that actually suspends the crystal off the substrate, you could now have ion diffusion through this precursor phase, and so it can add to the growth front at the base of your crystal. So if I draw out the full mechanism, we start with a supersaturated solution, and as is commonly observed in these polyelectrolyte systems, you form this kind of polyelectrolyte-rich precursor phase, and in my case, it forms on the substrate. Now, this precursor must allow the diffusion of ions through it for this mechanism to occur. And as we saw in the video, crystals nucleate off the substrate, seemingly, but in this case, I believe it's actually nucleating at the interface between the precursor and the solution. And the crystals grow in this way, where ions diffuse through the precursor and add to the growth front at the base of our crystal, so the crystal gets longer. Now, this makes a really specific prediction. It says that what I should see between the crystal and the substrate is some polyelectrolyte or PAA-rich phase that is suspending that crystal off the substrate. So to investigate this further, I look to do TEM. And I want to be upfront with this slide. This is a difficult experiment. I'm looking for a metastable, low-concentration phase that is rich in carbon and is beam sensitive. But we were able to get this cryo-TEM image of a biomorph growing associated with this amorphous phase. And this was all done on a silicon nitride grid. And if I take diffraction from over this hole here, you can't see it too well, but there's essentially two diffuse amorphous rings here. And if I look at this EDS pattern, I can see that this phase is indeed rich in carbon, but also oxygen, and with some sulfur. So this isn't a definitive phase identification, but it does say that there is an amorphous phase that's associated in that interfacial region at the base of the biomorph. Now, approaching this from another angle, we were able to fluorescently tag our polyelectrolyte, PAA. So anything you see here is, anything that's green is our PAA. This is what the crystals actually look like on SEM. And what we see in this image is that PAA has deposited all over the substrate. So the substrate is not usually fluorescent, but it's showing up green here because it's covered in PAA. And more interestingly, we actually see that these zones where there's very high concentration of PAA are located at the base of the biomorph, as well as PAA being seen continuously throughout the structure. So when we bring this all together, we have this optical microscope time-lapse showing that the biomorphs are apparently being pushed from their base at the substrate. We have this interfacial amorphous region shown with TEM, and we have the fact that PAA is enriched at the base of the biomorph. So now let's revisit those self-similar, the hierarchical structures that we saw before, and see if we can explain their formation. So here they are again, and I wanted to show that it's not just the exterior of them that looks hierarchical, and actually on the interior, they're also made from these smaller nanocones. So I slice through the crystal, taking a picture with each slice, and indeed I see internally they are made from nanocones. Okay, so they are actually hierarchical. And now when I look on the fluorescence microscope using that same technique where PAA is green, I see that the polyelectrolyte is not distributed evenly across the structure. It actually forms in these regions here, so there's bands of PAA that form along the self-similar structure. Now, if I take this with some 4D STEM data that I have that shows that the orientation of the cones is not transferred from one cone to the next, I can come up with a mechanism for how these hierarchical crystals form. So what's really interesting about this mechanism generally is that it's kind of like an extrusion mechanism. So the crystal can't be wider than the precursor from which it is growing. So in this case where we're forming a cone, we start with this narrow precursor, and we have this narrow wire or crystal coming from it. With time, the precursor grows wider, as does the cone, until we reach some point where a critical size is reached. So here, the precursor is now so wide that ion diffusion to the center of the cone, or to the precursor, cannot match ion consumption by the cone. So we reach this critical size and a depleted zone is established in the middle of our precursor. And this is where the really interesting stuff happens and you start to form this hierarchy. So now where new nucleation can occur, it's not going to occur in this depleted zone, and it's not going to occur outside of our precursor. So it's driven to this very small site where it's favorable to nucleate. And so we get this precisely guided hierarchy forming where these new nuclei push this old crystal up, and the old cone now terminates, it cannot grow anymore. And as it does so, it pulls this layer of PAA with it, and that was what we saw in the fluorescence images. So this is how hierarchy is established in this case. It's this cycling growth where growth terminates and then reproceeds as these new, smaller nuclei that push the old crystal up. Okay, so here I just want to demonstrate that this mechanism is not specific to strontium sulfate alone. Previously, I've just shown images relating to strontium sulfate, but my master's student actually managed to get this video of calcium carbonate growing in a very similar way. So here, again, look at this hooked structure at the end of the crystal. As it grows longer, that shape doesn't change. So this suggests this crystal is also growing at the base. So we were also able to produce these self-similar structures in the calcium carbonate system. And what this really means is that this is a general physical pathway guided by transport and interfacial regions that produces this hierarchy. It's not that we have to get involved with the growth process. We don't have to template. This is simply a result of the additive hindering growth and then allowing growth to proceed. Okay, so with that, I'd like to say thank you to my supervisors. Thank you to Badisha for tagging the PAA, and my master's student, the Bragg Centre for funding, and LEMAS and FBS. Thank you.
Thank you, and it was a fantastic talk second time round as well, a variation of first time round. Any questions?
So it reminds me of carbon nanotube growth a little bit.
Yeah, yeah.
And there, the size of the catalyst particle in the CVD process defines the nanotube diameter. So
exactly, yeah.
If you could modify the wetting of your PAA on a substrate, you could control the size of the crystal.
Yeah, so that's a really nice thing with this system. I'm obviously not depositing the catalyst. It forms spontaneously, but we can control how well it wets. So on glass, we tend to see these bundles of wires, but on silicon wafer, that's where we see these self-similar cones. So I've not really got to the bottom of it yet as to why exactly that happens, but there are these distinctions based off the substrate. Yeah.
You could do some contact angle.
Exactly. Yeah, that's next. Yeah, thanks.
We've got a new future plan there as well. That's great. Okay, in terms of time, we're going to say thank you very much, Oliver. Great talk.
Cool.
Thank you very much indeed.
Thank you.
And I'm going to hand over, the microphone's working, to Christoph to take us through our last session.
Thank you, Edmund. Well, yes, this brings us to the last session, and do I have to flick the slides? And it's a great pleasure to introduce Dr. Mark Bruce from Oxford Nanopore Technologies. Mark did his PhD some time ago in Surrey, where Mark is a sort of a protein engineer by training, and during his PhD he started working with nanopores, and I think that never left you really. Mark then joined Oxford Nanopore Technologies, which was a very small company at the time when he joined. I think you said you were employee 13. Yes, so they have obviously now grown to a much, much bigger company. And Mark has been with them for a number of years and is now, I wrote this down, I can't remember, Vice President in, what is he called? In sequencing method research.
Yeah.
And Mark will talk about nanopore sequencing today. Thank you very much, Mark.
Thank you. Thanks a lot for inviting me. It's a pleasure to share some of the work that we do at Oxford Nanopore. Say that title is a bit of a mouthful, but it essentially means that I get to play around at Oxford Nanopore, and they pay me to try and find new ways of using our platform or developing new technologies within it. So I'd like to take this opportunity to share a few of the bits and a few of the things that we do. I'm going to start off by giving a bit of a company overview and a bit of a history of the company, and try and relate this back to the first talk and the first session this morning, showing how UK innovation and startups and universities in the UK can go on to make a success. They can go from concepts to products to commercialization, all the way through to a fully fledged business. I'm also going to address the question as to what is Oxford Nanopore doing presenting at a material science conference? You think of nanopores, we do DNA sequencing. Why am I here? What am I going to talk about? And finally, if we've got some time, wrap up with a few use cases and a few examples of how we try and utilize our technology and how it's used in the wider situations today. So, Oxford Nanopore, the heart of it, we are tool builders. We are trying to build and provide tools to individuals to answer any biological question or any time they interact with biology in their life. So we are a spin out from Oxford University. We spun out just over 20 years ago. We are a R&D and innovation-led company. We've built a huge community of researchers and scientists through that time. Over 20,000 publications to date. It's getting harder and harder to try and keep track and see the number of publications that are coming up. Well, that has almost certainly grown since this slide was put together. But to say, at the heart of it, we are tool makers. We're trying to make sure that we can provide tools for individuals to answer their biological questions. Everything I'm going to talk about today has been built on numerous different collaborations and fundamental work that has been done through global institutes. We work with an awful lot of different institutions and universities. We try and sort of build on the fundamental science and the fundamental technologies and develop those into products. So what are we trying to do? So our vision is to try and enable the analysis of anything by anyone, anywhere. It's quite simple, but an incredibly bold challenge. By this, we want to make any time anyone interacts with biology or biological material, if you have a question, you want to know the answer to it. That answer should be simple, easy to access, and available to anyone whenever they want it. So I'm just going to start off with a fundamentals of how nanopore sensing works. I know a few of you will be more familiar with this concept than others. But it's a very, very simple concept at its heart. That we start off with a nanopore, or a very small channel, which sits between two chambers. That nanopore will have a current or an ion flow that goes through it. There'll be a unique signature. If it's a nice, happy, consistent signal, that means it's generally a good starting place, it'll be flat. As soon as a molecule or an analyte or anything comes near, by, passes through, or interacts with that nanopore, that electrical flow, or the ion flow, is altered or changed. So this squiggle will differ depending on exactly what's in or around or touching that nanopore. We can use this signal to infer what that molecule is. So all of this started from single channel experiments, and I think there's a few of these in the centre across the road. An exopatch, where this is a single channel amplifier, which is a very, very sensitive detector and can start recording picoamp measurements that go through a nanopore. So nanopores have been around for over, the concept of them has been around for over 100 years. Back in the 1970s was the first time that sort of single molecule measurements were done with patch clamp studies on nanopores. It was around the sort of mid-1980s where people started to think not just about can I characterize nanopores in their native environment, but can we start using these as tools, or can we start finding an application or use case for a nanopore? And a lot of concepts were flying around using them for filtration devices, using them for biosensors. And towards the end of the 1980s, David Deamer sketched down this concept of trying to use a nanopore to sequence DNA. So in a very similar setup to what I was just showing before, he envisaged having a DNA strand passing through a nanopore, and then as each of these bases were going through the nanopore, you'd get a different, distinct level from them. And then from this squiggle, you can identify what those bases are and sequence DNA. That is the fundamental concept and the building blocks that we've built all of our products and technology around. So we took that. We actually use a motor protein to help feed the DNA through the nanopore to make sure we've got consistent, controlled movement of it. As that DNA or RNA passes through the nanopore, the ion flow is disrupted and altered, and that generates this squiggle. So this is a little bit more complicated than the 4 steps and so on that were shown on David's drawing beforehand. But essentially, it's the same concept. The bases or whatever's in that nanopore will contribute to the ion flow and give a distinct signature of what molecules are going through that nanopore to then try and work out what the molecule is. So this is a bit of an overview slide, just showing all the different components and everything that goes into our setup. Very broadly speaking, we've got on the, I'm sort of getting my left and rights confused. On the left-hand side, we've got the signal generation side of it. So this is all about how we actually generate that squiggle and how we generate that signal. And then on the right-hand side, that's how we do our signal interpretation. So that's turning that squiggle back into a DNA or an RNA sequence. A lot of what I'm going to focus on today is going to be more on this side, but we do have a significant amount that goes on within the base calling and the algorithms and machine learning and AI side of things at the company as well. So with the signal generation, there's a lot of components and a lot of different parts that go into generating a clean, consistent, and robust signal. We've got the nanopores, we've got the motor proteins, we've got the sample prep, the run conditions, the platform. How all of these work together and how all these components behave and interface with each other is critical to producing a nice, clean, consistent signal. That signal can then get passed over to our algorithms to then interpret that and turn that back into a DNA or RNA sequence. The cleaner and the easier that sequence is to process, the more efficient and the better our base callers become. So I posed a question at the start as to why Oxford Nanopore here at a material science conference. Fundamentally, what our tools and our products do is turning a biomolecule into an electronic signature using the interface of a whole host of different materials. So what I'd like to try and run you through, and the core of the speech here, is about how we go via that process and how we try and turn a biomolecule into an electronic signature and the transformations that we need to go through and the materials that we need to use and interface on that way. So start off with DNA. The DNA needs to interface with a nanopore. It's not your traditional material interface, but you're essentially trying to make sure that nucleic acids interact and bind and behave when they pass through protein. We do an awful lot of work within the protein design space, treating protein essentially as a material or an engineerable material to try and make sure we can get good, consistent signal coming through from that. We've also got the interface between the pore and the membrane. So if the pore doesn't go into the membrane, then nothing works. If the pore starts moving around or jumping up and down or not sitting nicely in that membrane, then you start getting noise within that signal. So the interface between those two is critical to get a good signal coming out from that. The membrane itself poses a whole host of other challenges in that we've got to try and interface that membrane onto our flow cells and onto our chips. So we've got to make sure that the membrane can form over all of our channels, is consistent, is robust, and is the same over thousands and thousands of different channels that we have. The support structures that we use for this also then need to integrate with the electrodes and the electronics within our flow cells. And then the flow cells themselves have to all fit together, multiple different components go onto this, and then interface with the platforms to be able to make sure that that signal comes through the electronics, off the platform, and onto our base callers. So, first part of this is the nanopore. Anytime you choose a material to build a tool out of, there are trade-offs with what the physical properties are of that material. We had two main choices when we started off with nanopores as to whether we go down the biological route or the solid state route. So solid state pores they have their advantages. We chose to go down the biological route because we get single atom resolution, the ability to engineer these things and make them incredibly reproducibly. At the moment, solid state nanopores, there's huge advantage going on in that space, and it's something we are keeping an eye on. But manufacturability and trying to make the same thing again and again and again is still a challenge that's to be solved for the solid state space. Biological nanopores, you can make absolutely trillions of these things from E. coli or from other bacterial species that are all exactly the same every single time. Because we chose to go down the biological route, that means we now need a membrane or a support structure to be able to integrate that pore into our flow cells. So if you were to design a platform that you want to try and ship around the world, be stable throughout a whole host of different environmental conditions, be usable by a wide variety of different people with different experience levels, you probably wouldn't choose a membrane as a thing to stick on a component that you want to try and ship around the world. Membranes are generally quite, it's essentially a small soap bubble, and trying to ship or move a soap bubble, they pop, they burst, they're not very robust or stable. We spent an awful lot of time developing our own synthetic polymers to be able to create a membrane that was stable, it was robust, it was consistent, but it was also thin enough and flexible enough to be able to insert a biological pore within it. So we looked at thick ones and thin ones and different components and different mixtures of all of these. But one of our biggest breakthroughs was being able to manufacture and find a membrane material that we could use, we could utilize in a production and scalable process, while also interfacing with the nanopore. The other challenge of developing that membrane was then making sure that it fits on our flow cells and our platforms. So there's an awful lot of work, and you see there's a hell of a lot of micro-patterning and different variations that went into this to make sure that membrane, we could find the right material that would allow the membrane to form, would be stable, would be consistent, and wouldn't pop or burst either during sequencing or during the shipping or shelf life process. So we've got the pore, we've got the membrane, we've got the supports, we've got the ASICs, we've got all the circuitry, all the electronics that all fit together on that. We need to make sure that they all play nicely with each other and all interface well with each other. But the final part of the challenge is once we've built everything together, we still need to make sure that our platforms and the flow cells are capable of sequencing and moving DNA where we want it to. There's no point in having all of these materials interfacing nicely with each other if when you stick DNA into that flow cell, the DNA then sticks to a surface or goes somewhere where you don't want it to. So within all of our flow cells, we want to make sure that the DNA goes down to the membrane and into the pore. So we spend quite a lot of time looking at all the different interfaces that we have within that flow cell. If I to include this slide. You can see that there are a few different components that go into that, from the plastic at the top, the gasket, the ASIC and the chip, and the bottom structure to interface with our platform. We need to make sure that all of these not only interact with each other, but also don't interact with the sample as it goes in. We don't want that sample sticking everywhere else. We want that sample going down to the membrane and to the pore where the detection occurs. So when we're choosing the materials to build all of these structures out from, I say it's not just considering how well they behave with each other and how manufacturable it is, it's also that consideration of how they interact with the samples and the different sample types that we want to start detecting and start looking at. So a lot of the tools that we've built are essentially a material science-based product. We need to make sure that all of these different components interact with each other consistently. All of them behave, and all of them can work together in a seamless and harmonious pattern. Just to give you a bit of an overview of where we are to date with the products, we are a highly accurate single molecule sequencing setup, which is heavily reliant on all of those materials working together. A lot of our improvements that are coming through at the moment are all coming from upgrades and interfaces between those components and making sure that we're continually engineering and improving every single one of those. We are one of the few technologies that can directly detect modified bases. So at the heart of it, we have a biosensor. Our nanopore doesn't really mind what it is that goes through that. It doesn't know what an A, C, T, or G is until you train it and you tell our base callers what that signal means. Because we're utilizing the native RNA and DNA structures here, we can actually detect a lot more than just your 4 canonical bases. So we have the ability to detect a lot of methylated bases and a lot of other modified bases that are starting to become more apparent and more prominent within the field. The ability to detect these and show where they are is now opening up a whole host of new fields to understand what their functionality is and what their importance is. So it's this ability to see this extra layer of information is allowing more questions and more science to be pushed forward. We're also leveraging this ability of detecting modified bases to actually start marking up particular areas of interest. So a lot of targeted sequencing is interested in particular regions or particular areas of a genome or a transcriptome rather than sequencing everything. The ability to start detecting and looking at modified bases allows you to kind of focus in on certain parts of that genome and do targeted sequencing. We've got a few applications that are taking advantage of this modified base detection to drive down the costs and make it more accessible to others. We can also do direct RNA sequencing. We are the only technology that can directly sequence a piece of RNA without having to turn it into a piece of DNA. Again, because we've got this solid platform and a nice quiet signal, it allows us to start looking into more insights and different molecule types than any other technology out there. We've taken this concept and scaled it massively. So we started off with a single channel. We released our MinION product first of all, which is a pocket-held sequencer, if anyone does want to see one. I'm not doing products, but and scaled this all the way up to hundreds and thousands, and new ASICs, new designs, new flow cells coming through that are going to start breaking into the hundreds of thousands of channels and nanopores per flow cell. A lot of this is essentially a manufacturing and materials challenge. We start off with a single nanopore, and we need to try and build this into a flow cell and a chip that will allow high density, get hundreds of thousands of electrodes and electronics all packed into a tiny, tiny surface in a tiny space, while making sure that every single membrane is exactly the same, every single nanopore is exactly the same, and every single channel gives exactly the same signal that comes through from it. So to summarize where the platform is today, we are a highly differentiated platform which offers a unique insight and more information than you can possibly get from any other technology out there. It's rapid, it's fast, it's simple to use, and we're starting to make massive inroads into the accessibility and affordability angles as well, to try and make sure that this is available to anyone, anywhere, whenever you have a biological question. All of that has been built up from the materials and the different components that we all put together and interface between each other. I'd just like to highlight a couple of the applications and a couple of the use cases of our technology out there today. It is used in a wide variety of spaces. Let's say we have a portable sequencer. When people are having challenges trying to get the sample to the sequencer, we have the unique ability to bring the sequencer to the sample. So for a lot of outbreaks, people quite rightly get a bit nervous about sending potentially contaminated samples across borders or into other countries. So instead of having to send samples to a centralized lab or some other country, you just take the sequencer to that sample, and it gives you a much faster answer, faster turnaround time, and avoids a lot of the logistic challenges of trying to move contaminated or potentially contaminated samples around. The greater insights and the modified-based detection in particular is having huge applications within the human genetics and the transcriptome analysis. RNA in particular is a very complex landscape. Nearly 200 different modified bases are known within the RNAome, and we're starting to tackle some of those and starting to understand what's the different modifications are doing and the functionalities that are caused from this. I just want to highlight a couple of specific collaborations and use cases that we've got. One of my favourites and one of the earlier ones we did was a collaboration with NASA. This was a little bit of what we termed a hero project, in that it's not a huge market out there. There's not many people that do sequence in space, but we thought, what better way of showing the versatility or the ability to sequence anywhere than sequencing in outer space. So there are MinIONs up on the ISS, which are being used to characterize a lot of the microbial communities and microbial microbiomes of some of the astronauts up there as well. There is a future-looking project looking towards the getting samples from other planets or from other spaces and starting to detect new life. But fundamentally, this was one of the early collaborations that we did to try and highlight the portability of our platform. If you can use it in space, you can pretty much use it anywhere. Another one of my favourites, I seem to have a lot of favourites here, is the fast turnaround time. So our platforms have been used during brain surgery to characterize and start giving actionable information back to surgeons during a brain operation. It's quite an invasive procedure, taking a biopsy from someone's brain, and it's not something people tend to want to do more than once if they can avoid it. A lot of the traditional diagnostic methods for biopsies tend to require one operation to go in and take that biopsy, going away and then doing an assay or a test to find out how malignant or what characterised that tumour. And then depending on that information, they might have to go back into under the operation and then do a procedure. What we've allowed here is that characterisation to happen during the surgery. So within a 90-minute period, you can actually take that biopsy, you can characterise that biopsy, you can get some actionable information back from that, and then decide what to do during that initial operation, rather than having to wait a few days or go back and try and do that again. We're also doing quite a lot of work with the large cohort studies from the UK Biobank to Genomics England. Again, utilising the richness of information that you can get from our platform to try and further the databases and building up the information as to what all of these differences within the genomics, the epitranscriptomics, what they mean and what their functionality actually is. Last one is we also do a lot within the biomanufacturing or the biopharma space. So in the last few years, the mRNA vaccine space in particular has absolutely skyrocketed. These were fundamental for the world's response to the COVID outbreak a few years ago. At the time, the technology that was used to try and characterize and QC and check whether the vaccines that people were making were what they thought they made, whether they were pure, whether they were stable, evolved around quite a host of different equipment and different QC and analysis methods. What we've developed is a single platform that's able to replace all of these different techniques to give the identity, integrity, and purity and QC mRNA vaccines all under one platform, under one assay, rather than having to do this host of other assays out there. Last thing, at the heart of it, our platform is a polymer characterization tool. We started off with DNA, we moved on to RNA, and we're now looking at protein. in exactly the same context that you've got a polymer that's made up of different subunits, and you want to try and characterize or sequence what those subunits are. We've applied the same principles that we've done for DNA and RNA to protein. So, yes, protein is a little bit more complex than nucleic acids. That you've got more amino acids that make up the building blocks compared to the bases. And you also have a challenge of charge distribution. With DNA and RNA, you get a nice even charge distribution throughout that polymer. With protein, it's not always the same. But fundamentally, it's the same principle. You have a polymer made up of different units. You feed that polymer through the nanopore. The different units that are in that nanopore will cause different ion flows and a different squiggle to be generated, which we can then train our amino acid callers to interpret that signal and start working out what the sequence of that protein actually is. And in a similar vein to being able to detect modified bases in DNA and RNA, the same principle applies to post-translational modifications in protein. If you can train the amino acid callers to recognize that signal that's generated from these molecules as they go through the nanopore, you can interpret them and bring them back. This entire principle, I say, we've done it for DNA, we've shown it for RNA, we're on the way to showing it for protein, but essentially any polymer that you can translocate through a nanopore, you can generate a signal for, and you can train your base or your algorithms to recognize what that signal is. You can characterize polymers with nanopores. So, it shouldn't be animated. I hope I've given you a bit of an insight into why Nanopore was presenting at a material science conference. But I also want you to start thinking about a world where we've got one platform which can start interrogating any single biological question you may have, whether that's looking at DNA or RNA or protein or other biomolecules of interest. We're on our way to creating a single platform that can enable any biological question to be answered and get that data to you as quickly as possible. Thank you.
Thank you very much, Mark. Any questions for Mark? Was that a question, Edmund?
Thank you. Really, really lovely talk. My question was, so the first slide you had was getting in surgeries and vets and all this. So how far away are we from that sort of thing, and what does the sort of price or the how do you need to get on that journey?
We're already on it. So there's one of the big transitions is showing that things can be done within a research environment compared to how you actually action those and put them into a clinical and a diagnostic environment. The fundamentals of showing that it can be done in a research environment have absolutely been done. We're now on that journey within that translational space and making sure that we get all the regulatory requirements in place to be allowed to actually action and use that information within a clinical setting.
Any other questions, Ashley?
Are you able to sequence single-stranded DNA or like sets of oligo pools where you're not entirely sure on the input sequences of all your DNA strands?
It's possible. All you need to do to be able to sequence with our platforms is being able to attach what we call an adapter and a motor protein onto the end of that strand. So as long as you can attach an adapter on there, you can sequence that DNA, whether it's single-stranded or double-stranded. So you don't necessarily need to know the sequence to be able to sequence the sequence of your sample to be able to identify what it is.
Thank you. So whenever in the past I had to sequence something with long reads needed, my understanding is that there's two technologies, Illumina is against you, right, with the kind of circular sequencing option, and then you guys can do quite long sequencing, but the quality of those reads is not always perfect because you're reading a really long sequence. I was wondering if you guys are developing anything to read the same thing, like multiple pores following each other.
So very interesting question. I'd love to pick this up with you. The accuracy conversation is an intriguing one. Our approach to this is we can sequence, the longest piece of DNA that's been sequenced on our platform is over 4 megabases long. That is a few orders of magnitude bigger than any other technology that can do that. We take the approach that we want to try and get that sequence right the first time. So if you can sequence it right the first time, you don't need to reread it, you don't need to have multiple passes. You can get that information straight off much quicker than you can ever do if you have to try and move things around or alter that. It is possible to do that on a nanopore. It's just the approach that we're taking is to try and make sure we get it right the first time. The accuracies I've showed there are actually about 6 months old. So the accuracies that will be coming out will be significantly higher than that and are comparable. Again, it depends on exactly how you measure accuracy and exactly how you want to slice and dice positional accuracy compared to whole molecule accuracy or structural variants or modifications and so on. But our accuracy is comparable with any other technology.
Do you understand enough about what specific design elements in the protein pore contribute to the highest resolution so that you can just design a protein pore these days, with Rosetta and AlphaFold rather than have to, retrieve whatever you get from nature?
Yeah, that's a fantastic question. We are doing an awful lot in the enzyme and the protein design space, utilizing tools like AlphaFold and as well as a lot of the other machine learning tools that are being developed in there. We started on this journey about 6-7 years ago. We were very early on within the machine learning. We had a machine learning group that was essentially doing all of our algorithms and our base callers. And we very quickly asked them to sort of pivot or have a small subgroup to start looking at the protein design space very early on. Not only is it all the ML tools, there's also a lot of molecular dynamics, or MD, that's looking to try and simulate or trying to look at in silico as to how do ions flow through a pore? How do you start modeling that? How do you start trying to predict what shape or what particular structure would do to an ion flow through a nanopore? It's a very exciting field, but I think it's still very early days. You can get some very crude, you stick something big through a nanopore, you can get a bigger blockage and a lower current. The subtleties around that aren't always clear at the moment, but it is a very, very interesting field that I think is going to move forward incredibly quickly in the next couple of years.
Good. Before we move on, can I just ask one very quick question? When will we see a protein sequencer? Next year.
You can sequence protein on this. We just haven't released the product yet. We are working on that protein sequencing product in-house at the moment. I can't give timelines for when it will be released, but we want it to be out there as quickly as we can.
Given that's in your pocket already, it's probably going to be very soon. Good. Can we all thank Mark again for a very fantastic talk? Thank you very much. Thank you all. Our next speaker in the session is Julia Gala de Pablo. She has done her PhD here in Leeds with a group of Steve Evans, working on Raman confocal spectroscopy for single cell analysis. She then moved on to Japan, where you did postdoc for I think about 3 years, is that right? 2 years? Has now come back to Leeds, luckily, and has been working on a number of different diagnostics applications. And today she will talk to us about gold, what are they? Nanopine cones, yes, for diagnostics.
Thank you very much. Can everyone hear me at the back as well? Yes, fantastic. Okay, lovely. So yes, today I'm going to be talking about gold nanopine cones. It's a good name. Used to be a postdoc in the group, and she was really good at naming these funny shaped gold structures. So I'll be saying that word many, many times today. So I've already been introduced, so I think this slide is not necessary. But this is just to kind of show my background. I did biochemistry and physics as an undergraduate, and then I jumped into biophysics. So I'm really interested in biological problems, but
I try to use physical tools to address them. This is just a bit of a summary of some of the things that really interest me. The main problem that I am trying to work on is cancer progression and cancer therapy resistance. I've done my share of microfluidics, and I'm mostly known for my work on Raman. And I'm now jumping a bit into a different type of Raman, which I will briefly touch today for clinical biosensing. And I wanted to mention about this facility. Has anyone here heard about this facility? Okay, we have a few people. And I'm hoping you guys can, everyone here can know about it and a bit about what it can do. So this is an image from the cross-section of a full artery from a rabbit that was partly blocked by an atheroscleral blockage. And this is completely label-free. So Raman is a beautiful technique, is really good for characterization of materials, but it's always been quite weak. But now we have access to an amazing technology for coherent Raman, so we can actually do very, very quick Raman characterization in a label-free manner. And this is, our new facility is based on the basement of Bragg building, so very near where the electron microscopes are, and we're accepting applications. So if you search for hyperspectral bioimaging facility, you can come to our website, and at the bottom there will be an access form. We have helped a lot of people in medicine, biology. We've had a few applications from physics, but we haven't had that many applications from material sciences, and we're hoping more people will want to jump in, especially because you're already using Raman in your pipelines. So moving on. Today I wanted to talk about nanoparticles in biosensing. They are currently already used. Everyone's seen a COVID test or a pregnancy test. Those lines are actually the color comes from the nanoparticles, but they could be better. They tend to have poor sensitivity, which means we need more of them to be able to see the lines. And this results into higher costs because you need more gold and you need more antibody to be able to see what you're trying to detect. And so in response to this, there's been the development of many, many different gold nanoparticle shapes that can be more or less complex in the literature that can give you better properties than the typical gold nanoparticles that are used in these tests. However, the synthesis is usually quite complex, requires high temperatures, and sometimes some nasty solvents, which makes scalability quite hard. So I wanted to talk about this specific nanoparticle architecture. And I think one of the best things of this nanoparticle is that most people could already make it in their labs. So this is how we make it. We just get a gold precursor. We mix it with a specific dye, which is called methyl orange. We wait for a tiny bit of time, add some sodium citrate, and then incubate at room temperature for 30 minutes. And we've been playing with this temperature a bit, I'll mention. And there, that's it. It's made. So what we think is happening here is that this dye has an apolar and a polar part, and it's self-assembling, and it's because we added to the gold at the beginning, is probably nucleating the gold formation into these self-assemblies, and that's allowing the gold to grow into kind of shapes, flake forms. And so if we wait enough, what we think is happening is that it's degrading and eventually giving us this sort of gold nanopine cone architecture where we have a bit of a rough surface. So we're not using high temperatures. It's a single pot synthesis. It doesn't need any nasty solvents, so it's relatively green. Minimal specialist equipment. Here we're using a centrifuge to wash them, and just 3 reagents. So for someone that's never done nanoparticles, as an intro to nanoparticles is not bad. So here, what I'm showing is the UVV, so the absorbance spectrum for these gold nanopine cones versus some gold nanospheres. You can see that gold nanospheres, especially the smaller they get, they usually have quite a sharp absorbance peak, whereas these gold nanopine cones have a much broader absorbance, which gives you higher scattering, higher visibility. They just lower concentration of them will be more visible. And here is an electron microscope image of them. Now you understand why they're called nanopine cones. They do kind of look like nanopine cones. And for these specific properties, this is the sizing. These ones were about 120 nanometer size. So are they any better for lateral flow devices? So this is some of the work done by Joe and Joel over here. This is for a model lateral flow device. So this is the typical pregnancy test. What you usually do is you have your sample, which may have the presence of this enzyme, human gonadotropin. And what you have here is a small pot that contains our gold nanopine cones that have either anti-hormone antibodies or just a general antibody. So when this flows through, when they get into the test, they will bind an antibody against this hormone if the hormone is present, and no matter what, they should bind the control line, right? So we're all familiar with this sort of test. We've all done at least once in our lifetime, the COVID ones, right? So what happens if we keep the concentration of gold exactly the same and we play with the antibody concentrations and the hormone concentration? So this is for spherical gold nanoparticles. For a concentration of 100 milliunits per milliliter, which is about the amount that a pregnant woman will have after 4 weeks, what we see is that the spherical gold nanoparticles do show the test line, but if we start reducing the antibody, at some point we lose it, right? If we have a lower concentration, which might be what you have after a couple of weeks, it's completely gone. However, for the same amount of gold, sorry, this is just quantifying that limit of detection for these spherical nanoparticles. However, for the same amount of gold, these gold nanopine cones do show the line much further for the higher concentration of hormone. And for the low concentration of hormone, they can also detect it. So when we actually quantify it, we can see that we have up to 20 times increased sensitivity. And this is because of this complexity in the shape that's giving us better properties in terms of absorbance and scattering. And so can we tailor this to whatever needs we have? And this is what we were doing here. If that last temperature bit of our synthesis changes from 10 degrees all the way to 35 degrees, what we see is that we can actually change the size of these nanoparticles that result from this synthesis. So we have good size control with temperature. And because the size determines also the UVV's properties, we also have that the maximum peak position shifts towards the near infrared the bigger the particles become, which means that we can now have nanopine cone rainbow, right? So we can have all these different colors, which might not be the brightest. I mean, they're a bit diluted, with all different properties in the UVVs. And we can actually characterize how these different sizes change our sensitivity. So this is showing particles looking at 10 degree, 20 degree, and 30 degree. And because the 20 degree and 10 degree were quite sensitive, we also made a test with 2 different color lines, which means that you could then make a multiplex test so that depending on the color of the line, you would get one result or another. And because we can now tailor the properties of these nanoparticles, depending on how we synthesize them, we actually can shift this peak all the way to the near infrared and try to use them as photothermal agents. So photothermal therapy, for those of you who have never heard of it, consists of adding an agent that can produce heat into a tumor and use that to overheat the tumor in a local way so that the tumor dies and the nearby cells are spared. So Xinyu did these experiments. She characterized how much heat these particles can produce depending on how much light we give them. And she actually put them into cells. So I don't know if you can see the red very well, but basically, these are pancreatic cells. Pancreatic cancer is really aggressive, difficult to treat, so it's a good model for this. And what we can see here is in the laser control, which is a 800 nanometer laser, so near infrared, the cells don't care. However, if we add the nanoparticles, we can very effectively produce this heating and then kill the cells. And similarly, we can do this with spheroids, and we see very similar results, causing some disruption of these spheroids if we treat them for a bit longer with a laser. And you might be wondering, why did I mention anything about Raman if I'm not talking about Raman? So here we go, we talk about Raman. So this is just a quick introduction. I think most people here seem to know what Raman is about. but I'll just explain it very quickly. So imagine a model molecule like CO2, right? And we're going to have some charges in different parts of the molecule, so the electron cloud will have a specific shape. Now, we often imagine molecules like they're stationary, but actually molecules are always vibrating, and we can separate these vibrations into eigen vibrations, so the individual vibrations, and they all come together into whatever the molecule is doing at any given time, right? So the Raman effect is proportional to how polarizable a molecule will be as it vibrates, okay? So let me explain. When this molecule vibrates, the electron cloud changes around itself in a symmetric way, which means that at the center of that vibration, this polarizability, is how much it can polarize in response to an electric field, has a zero slope, which means this will not be a Raman active mode. So oftentimes people think that any vibration will be Raman and infrared active. That is not true. It needs to have this exclusion rule. This is another example. Similarly, that slope is 0 at 0. We don't have Raman. However, if this slope changes, so if this molecule becomes more polarizable with the vibration, then what we'll have is the Raman effect will be active. What does that mean? It means that if we have a laser and it interacts with this molecule, most of the photons are going to just scatter the same. So we call that Rayleigh scattering. They will have exactly the same energy. And some of them will lose energy. And the energy they lose will be proportional to the energy of the vibration. So you can connect directly that vibration, which is a signature of that bond, with that laser light. So if you prefer the Jablonski diagram, this is basically how it looks. You would have your energy levels, and you would have the incident laser line, and it will scatter down into a higher energy level. The molecule will look like it's vibrating with the same frequency, just a slightly higher amplitude. Does that make sense? So what does this have to do with nanoparticles? Well, there's actually a very nice effect when you have a nanoparticle interacting with an electric field if certain conditions are met, which is that you can activate the plasmons of the surface of that specific nanoparticle, which just means that the electrons in the nanoparticle can now start vibrating, being activated by a dielectric field. And that will happen more effectively if you're in resonance. And what that results in is a very, very strong electric field near the surface of that nanoparticle that will have the same frequency as the incident light. Now, what happens is if you're trying to do Raman on a particle, and you have this super enhanced electric field, and I'm talking 4 orders of magnitude enhanced, all of your Raman signal will basically come from here. And people have been able to actually do up to single molecule Raman just by exploiting this effect. So if you have a gold nanoparticle that has this property and you manage to excite this plasmon, you can get what we call surface enhanced Raman scattering and get really, really strong Raman signal. So how do we know if we are in the right regime? So in order to try to answer this question, we went to the EM facility and we asked them if we could do some electron energy loss experiments. So this is what I'm showing here. So this is one of our gold nanopine cones. And this is the electron energy loss spectrum. So this would look like a big peak, and this would be the tail, where this is the energy. The peak would peak at 0. And the raw data is shown in this kind of green color. The background is in red, and the edge is in green. And depending on where you look, so this was mounted on a carbon grid. So if you look at the carbon grid, you see the carbon peak, which is nice and reassuring. If you look at the background, you just see a featureless shape. And when we look at the gold nanoparticles, we actually see all these really nice peaks. And if you zoom in into this area over here, we can see this little peak here near 2.5 electron volts. So these peaks actually agree beautifully with bulk gold, which is quite nice. But what we also see is that this peak here, we believe is actually measuring that surface plasmon that happens around the gold nanoparticle. So you can see it peaks around it as a halo, and it does have the energy of an optical plasmon. So you can actually see this plasmon directly, because if you wanted to simulate these nanoparticles, you would need to know exactly their shape, and you can see how complex they are, right? So how would you simulate it? But we can actually directly measure it. So this is kind of hot out of the press, and we're still understanding this data. If you're interested, please come talk to me, because I'd love to chat more about it. And we can see some of the other bands, which are also gold associated. There's also a carbon band over here, so you can see the carbon grid shows in some of the images. And these ones will be interband transitions, so they're in common for like both gold as well, but this one is the plasmon. And you can show this bit of the spectrum against wavelength instead of electron volts. So another way to show energy. You can overlap it with that absorbance spectrum. So this is kind of how it's looking right now. We're trying to understand it. But what we think is that we could then get the information of what's the exact light that can create the strongest plasmons from these nanoparticles from this. And so are these good for Raman? So that's what we went on and had a look at. So this is what I'm showing here. And this was actually quite surprising because we got the nanoparticles fully synthesized, washed many times, and they shouldn't have any signal because they're by themselves. And then we got an insanely strong signal of methyl orange. So it turns out when we synthesize them, they're actually covered in methyl orange. And because we get this SERS enhancement exactly on the surface, we are getting this super strong signal of the methyl orange that is strongly bonded to the surface. And we can switch it off if we do a ligand exchange. So if we add, just as a random ligands, this is 11 MUA, so 11 carbons, we can remove this really strong signal. So basically, we have these gold nanoparticles that we can see super strongly and super specifically in Raman right now. So we're currently working to try to develop a SERS assay in collaboration with the School of Cardiology, so in the context of diabetes. So that'll be all. I hope I transmitted how cool these nanopinecons are and how anyone could basically make them with basic lab equipment. I'd like to thank Steve's group and a few scientists within, Joe, Joel, and Xinyu, who have done most of the work. And from my slowly growing lab, Daisy has been trying to get this SERS assay working from then. So thank you very much. And any questions?
Any questions, anyone?
Right, thank you. Yeah, it's a very interesting talk. Yeah, when you do the natural flow device detections and you find your nanopinecone is more sensitive than the spherical gold nanoparticles, are they simply just said because your nanocone is much bigger, so it has a much higher extinction coefficient that would make your basically natural flow devices more sensitive that way? Or?
Basically, but it's using the same exact amount of gold. So at the same price, you're getting a much better reading, if that makes sense. So you're using the same amount of gold, but you're getting a better reading. But yes, it's mainly because you have better extinction coefficient, yeah.
Is it also because you've got a very rough surface, so there's more binding sites?
That is a good question. I mean, these were compared under the same antibody incubation, but it could be that they're taking up more antibody than the gold nanospheres, so it's possible.
Is it just rough, or are they porous?
We don't know. I think Steve thinks they might be porous because if you use this similar synthesis under different conditions, he's actually been able to make nanosheets, nanoseaweeds, and so on. So what he thinks is happening is these nanoseaweeds are coming together in a bit of an aggregate. What we see with the ligand exchange is we can actually switch off the SERS signal quite abruptly. If there were pockets inside, we would only be able to do that if it was so porous that we were able to chemically access it. So it might be porous, but then it would have to be, yes.
Big pores.
Yes, big pores.
Yeah. Any other questions? Can I just ask a question about sensitivity? So you said you had a 20 times increased sensitivity on these devices. Lateral flow devices are usually not very sensitive for a lot, and not sensitive enough for a lot of sort of biomarker detection applications. Do you think with a 20 times increase, you get towards being able to have to make lateral flow devices which can sort of be sensitive enough for lots of biomarkers that are so far inaccessible for lateral flow devices?
I think
is the 20 times good enough?
I think it could be. To be honest, I guess case by case you would have to look at it. But I think even if not many biomarkers can be accessible, at least you could make much cheaper the current tests because you would need less antibody, less nanoparticles. So I think probably both. So yeah, it would help.
Okay. Thank you very much, Julia.
Thank you.
We are coming close to the end, and we have got one final talk left, but I can tell you it's a very good talk, so it's not wasted to stay. Dr. Tim Luxton did his PhD in FBS at the University of Leeds, where he developed sort of an approach for detecting small molecules. When I say small molecules, I mean molecules which are sort of less than a kilodalton, sort of 500, 600 dalton in size, which is very difficult. Tim has moved on and sort of has now been working on the analytical validation of these tests, and he will talk to you today about using these tests to make personalized dosing of therapies more accessible to a much larger range of the population. Tim.
Is that okay? That sounds better. So with too little antibiotic, the microphone doesn't work, and it might drive antimicrobial resistance. With too much antibiotic, you can have toxicities, including seizures, confusions, and things like that, which is obviously not very good. So here we have a 32-year-old patient with cystic fibrosis. He unfortunately has a multi-drug resistant Pseudomonas infection, and after 4 days of a first-line antibiotic, he was escalated onto meropenem. He had elevated creatinine clearance. So creatinine clearance is a measure of renal function, so how well your kidney is eliminating things from your body. So this means that this patient is eliminating more drug from his body than a normal patient would. So that means he might need more drug. He also had a C-reactive protein, CRP level of 17.7 mg per deciliter. This is a biomarker for infection. And as you can see, a normal CRP level is less than 0.5. So he indeed did have an infection. So meropenem was monitored daily. He had the maximum approved dose straight away, and this resulted in meropenem trough levels of 1 to 2 mg per liter. So right at the end of his dose, he had 1 or 2 mg per liter of meropenem left over in his system. For a multi-drug resistant Pseudomonas infection, we'd want to have 8 to 16 mg per liter. So he's quite far below the right range. So he was switched to a continuous infusion. So this is the same amount of antibiotic, but continuously flowing into his body rather than discrete doses, and this elevated his meropenem level to a good range, between our 8 to 16, even above. And that stabilized his renal function. So now he had a bit more of a normal renal function. This unfortunately wasn't the end of the story for this patient. And on day 17, he was allocated a new lung and underwent a transplant. Unfortunately, this new lung came along with another bacteria, a multi-drug resistant bacteria, and now we want meropenem levels above 32 mg per liter. So this was a really nasty infection. So he was co-administered tigecycline, sulbactam, colistin as well, with a higher than licensed meropenem dose. Unfortunately, with therapeutic drug monitoring, where they're measuring the amount of meropenem every day, we had meropenem levels above 32 mg per liter, and thankfully this patient went on to be transferred to the general ward, and he recovered from his infection. This is a really positive story, and unfortunately is not the case usually, because typically you can't measure meropenem levels or drug levels, any drug really, every day. There are some drugs you can, or it's much more accessible, but for most drugs, this isn't possible. So we have developed a new way to measure small molecule drugs, which hopefully will allow this kind of therapy to be carried out in any clinical setting. This work, of course, is not a one-man show. There's a whole host of researchers that have helped us, from the phage display lab. We have clinicians like Dr. Jonathan Sando and Richard Gould, the mass spec guys in chemistry, which have helped develop a comparative assay. And we've also worked with an industrial partner, MedTech to Market, who are hopefully going to help us take this forward. So personalized dosing, hopefully you got a good picture of it from my case study. So for most patients and for most drugs, each patient gets a standard dose. Unfortunately, there's a growing body of evidence which is showing that a lot of patients aren't getting enough, and a lot of patients are getting too much. So by measuring a drug, we're able to optimize the dosing and personalize their therapy. We surveyed a number of clinicians about personalized dosing, particularly of meropenem. At the moment, even for other antibiotics as well, they have a 2 or 3 day turnaround time from sending their sample off to get a result and receiving their sample back. So rather than every day, maybe it's every 3 days. And that's because there's maybe only 2 or 3 facilities in the UK which are carrying out clinical therapeutic drug monitoring of small molecules. For antibiotics, that's down in Bristol. And we had one quote from a clinician that I always like to use, which he says, therapeutic drug monitoring is like predicting the past. It's just too slow to get a meaningful result back. And that's mostly due to the fact that for clinical therapeutic drug monitoring, the gold standard is mass spectrometry, which necessitates centralized facilities. You have to send away samples, which includes logistical problems, degradation of the sample, so you might not have the correct result at the end of it. Meropenem has quite a short half-life. So you need to send away samples, you can't get the result back. Other techniques include competitive immunoassays. These are typically not too sensitive. You are switching off the result when you have more drug rather than switching on the result. And there are other techniques such as Raman spectroscopy, which are, I guess, coming into the clinic. So this is an antibody, and this is to really demonstrate why we can't have a nice sandwich ELISA with the kind of pregnancy hormone. Pregnancy hormone is about 40 kilodaltons, so you can have a lot of chemical space to have one antibody bind and a second antibody bind to give you a result. For our meropenem, it's just under 400 daltons, so there's not much chemical space for that meropenem to bind to an antibody and a second independent antibody to also bind. We have got round this problem through our new technique and we're naming this the detection of induced structural change. So we're utilizing the natural target for these drugs, natural binding proteins, which have a natural affinity and a natural specificity for the active molecule. So immunoassays also have a problem of promiscuity to degradation products and metabolites. Because we're using the active target protein of these drugs, we're getting around that issue as well. So here is LDT-MT2. It's a transpeptidase from tuberculosis. And when you introduce meropenem, you have this small structural change around the beta hairpin loop in the active site. And the phage display team here in Leeds and Asbury have selected an adheron protein or an affimer protein that is specific to that structural change. Our collaborator, Robert Schnell, in Karolinska has got us these really nice crystallization data. And we can see from this crystal structure data that we are indeed binding to the structural change rather than the meropenem itself. There's no actual direct interaction between the meropenem molecule and the adheron. And when there's no meropenem present in the unbound conformation, there's a tyrosine that blocks the variable region of the adheron from binding. So we can use this natural binding protein, LDT-MT2 in the case of meropenem, and an adheron to have a two-element binding and detection system as with a sandwich ELISA. And then we're able to produce sandwich ELISA type assays to measure meropenem. This is in 100% serum spiked with meropenem and measuring meropenem on a standard lab absorbance plate reader. So these two kind of reagents can then just be put into clinical diagnostic machinery that's already present in pretty much every clinical lab. And we've taken this one step further by measuring meropenem accessibly. We're using a split luciferase assay here. So this is all in solution, there's no wash steps, and this 15-minute test, we're able to measure a really broad range of meropenem. If you can remember back in the story earlier, we were wanting to target 8 to 16 mg per liter and then up to kind of 32 mg per liter. We're well within that range. And also into the kind of toxicity range and the subtherapeutic range as well. Not only that, because we're producing a light signal, we're able to measure meropenem very easily with really low-tech solutions. So these blue dots are different concentrations of meropenem. And I've just taken that picture with my phone camera and maybe enhance the contrast a little bit just so you can see the blue a little bit better. So personalized dosing is really needed and important to improve drug treatment. Current methods are not really feasible for widespread clinical use. We need to send samples away or send people to the mass spectrometer. In Norway, for immunosuppressants, they send all their patients to Oslo and house them in a hotel for kind of 16 to 20 weeks to carry out therapeutic drug monitoring. If we can use this technique for kind of accessible measurements, instead of sending patients to Oslo, we can have them in their homes with their friends and family around. So DISC, the detection of induced structural change, can specifically and sensitively measure small molecules, and we can do this with really kind of low-tech equipment, hopefully introducing personalized dosing to any clinical environment. Thank you.
Thank you, Tim. Any questions? Can I ask you a question? Is this approach, is this transferable to other small molecule drugs, or is this specific to antibiotics or beta-lactams?
No, it's definitely transferable. We've got other assays for other antibiotics, and we've got lots of strategies for other drug classes. So pretty much for every drug that I've looked into, we've developed a strategy to use DISC to measure that drug. And yeah, we're working on that and trying to get funding for that.
Edmund.
So looks really good. So what is the sort of next steps, and how long do you think the next steps are going to take? So your map there with the crosses on, how long is it going to take to get those crosses in place with this equipment? Do you think?
That's a really good question. Yeah, also working on that. So we've recently got a grant to get our meropenem assay into the LGI, not to test on patient samples, but Christoph's blood, in particular Christoph's blood. He's going to go up to ICU and intensivist is going to take his blood and we're going to spike it with some meropenem and then basically see how this fits into the normal clinical pathway. Because personalized dosing is actually quite a complex intervention. You have the kind of timing of taking the sample, you have the timing of when the last dose was given, when is the next dose going to be given, and kind of storage of those samples, sending those samples. So to kind of put our test in that environment and see how long it takes, can we get that turnaround time okay? That would be really interesting. And we're also working with MedTech to Market to try and get this into a UKCA approved and CE marked and things like that. But timeline, I don't know the exact date.
Any other?
I mean, could this technology ultimately be like some sort of implantable dosing thing where, you know, the signal drops below a certain level and then some actuation happens to release a further dose or something?
Yeah, that's a good question. For like a continuous monitor and yeah, maybe in the future, that would be very cool. At the moment, I think the route of least resistance is to get it into kind of clinical labs, and then it potentially a point of care test, and then, I mean, yeah, if it's kind of on a patient already, then you get around the sampling and you kind of have the timings and everything, so that would be really cool. Whether it's reversible and reusable is another question, and it will probably be kind of application dependent.
Good. I think that brings us to the end of the session. Thank you very much, Tim. And I'm going to hand over to Evan now.
Hand over to me. This is right. I think we're going to have a short intermission here. This means do not disappear because we're going to have prizes, but we just need to extract, I think, the advisory board outside very, very quickly, and the Bragg team just to get our prizes in order while I do something to keep you happy. And apparently there's a slide I'm meant to be showing here, so you can see I'm not really on track. So the advisory board, if you could just go outside. Right, the Bragg Exchange, right. Okay. This is the slide I'm meant to be introducing, which no one's told me was on this slide, so we're going to read it and as we go. So let's just go round the list here then. So next lunch at Bragg, 11th of February, a technician specialist network, so particularly for our technical experts, but I guess anyone else who's interested in that. And then 12th of March, Innovate UK, and I think that's a lunch at Bragg as well. I've got that right. So QR codes about that. The Materials Research Exchange, this is organised by Innovate. Royce are very much part of the organisation of that. That is in London on those, it's 2 dates, I think. It's 19th, 20th, is it? Or so, but the Materials Research Exchange, it's a good chance to see a whole set of organisations talking about materials research. There will be lots of people interested in materials research from companies, industry, from investors there and from funders. So it's an interesting event to go to. Bragg will be at that event, as will Royce. And if you have particular companies you're looking to make contact with, do let us know. And if they're there, we can do that. But usually it's a really good event for meeting up with companies. There is some funding support our members. There's money for RTPs, research technical professionals going to conferences. There's money for if people want to get a number of Bragg people going on tour. Don't get too excited by that, but that means going to visit one of the national institutes like ICE, these type of things, synchrotrons, or going to a company. Come with some ideas. And if you're a PhD student, remember there is some funding. It needs to be applied for by your supervisor through Bragg to help support going to conferences. PhD colloquium, I mentioned that earlier, but I didn't have the date. It is apparently the 16th of June, so please do book that in if you're a PhD student, or if you're not a PhD student and have PhD students, encourage them to come to that. It's usually a really good event with a whole range of PhD talks, and usually we arrange 1 or 2 other things to go with that. And our commercialisation and industry drop-in centres in the Bragg building, the next 2 ones are on 11th of February and 11th of March. So if you've got ideas and things that you just might think might be helpful for commercialisation, please do just drop into those. So I think that's the sort of things coming up, and we will, before long, be thinking about Bragg Exchange 2027. So dates in January, don't cite too much at this point, Giles, but dates will go in for January 2027 very, very soon, because we're being asked whether we should book it up already. So some events coming up with the Bragg. Is there another slide after? There is another slide after this. This is great fun. What have I done with the clicker? I've lost the clicker. See, I'm making up time very well. Right. So we've got two things here. Bragg Centre membership application form. So if you've come to this but aren't a Bragg member, and you don't have to be within the University of Leeds to be a Bragg member, you want to be on our mailing list, then the left QR code should take you to that, and please do join the Bragg membership, because then we can tell you what we're doing and tell you also what Royce is doing, and other materials opportunities. And the right-hand side is a Bragg Centre membership survey. That's not specifically about this exchange, but we really would like to have comments and views and suggestions from our membership, because actually we're trying to do things to help our membership. We need to hear from them. So there are 2 QR codes there, and if you're just waiting for them to make the big decision about who has won what prizes, then you could just fill your time in by doing that now. Is there another slide coming? There is. This is exciting, isn't it? Right. It's the Royce. What am I going to say about this? So, the Royce. How many more slides are here? I wish I had a look. How many more after this? Sorry? Quick peek what that is going to be. Right. Okay. So, to remind you, we're part of the Royce Institute. Leeds has been a founding partner from the start of it. Royce does 3 or 4 very important things, and these are illustrated on the right-hand side there. So the top is really the national materials, presenting materials and highlighting materials, because quite often we see the end-user applications of materials that government and people understand. A communication system, we understand what that is, or a medical device. But underpinning this is materials. And so Royce is doing a large amount of work, and the National Materials Innovation Strategy gave us some indications of the areas of materials we're working with and presenting that to government. So it does national foresighting. It helps catalyse collaborations between academia and industry, and we, the Bragg team, can help you with that. There are some facilities and capabilities you can access through the Royce, and then skills development, outreach and engagement. And those 4 activities Royce is involved on behalf of the UK materials community. We're part of that, we're all part of that, and do get involved with Royce, and do come and speak to us as a Bragg team to know more about how you can get involved. And my final slide, because I've seen people coming back into the room, so I'm hopeful, but I haven't seen the people with the certificates, so I can keep going for a bit. Is do share your Bragg Exchange experience. So please do all you need to do on your social media. And Claire is smiling at me because she knows I'm totally incompetent. But all of those who are competent, please do share your experience of Bragg Exchange on social media. We would really appreciate that. So overall, please do give us feedback and help. And fortunately, I now see, just in the nick of time, people are the team is arriving here to come and do prizes. Right, are we all ready over there? Okay, now I'm going to do something, since everyone is here now. I now want to move away from the slides. I've done the bit that I was told to do, but now I do want to do a few thank yous before we actually move on to the prizes. And I'll do the thank yous first, otherwise once you've got your prize, you'll disappear. So, firstly, thank you to everyone here and everyone here yesterday. It really has been a fantastic exchange, a really wide range of materials, both presented in the talks and the posters, and a big thank you to everyone who's made part of it. It is you that make this such an exciting event. I can't go much further as well without thanking Claire, Lucy, Steph, Faye, and particularly Helen, who has really picked up a lot of what we've been doing from planning last January all the way through to here. Thank you very much, all of you. You know, I don't know there's a better team to work to put the exchange together, but thank you all very much for making this such a success. So please, can we just have a round of applause for Bragg Group. I'd also like to thank our external advisory board who have been asking questions, going around, seeing posters, give us advice as a Bragg Centre. Really, really do appreciate you coming and sharing and giving your time to us. Thank you very much indeed to our external advisory board. We've just mentioned Royce and what Royce can do, but Royce also provides funding to the University of Leeds. I'm really grateful for that, which helps us put on conferences such as this. So a thank you for Royce. We don't have a representative here at the moment, but a big thank you to Royce. It really is doing a lot for the national materials innovation in this country. And then finally, we're going to come to prizes. So the RSC, Space Hub Yorkshire, thank you very much for the donations to the prizes. We're going to get you on stage in a minute. And then it's also been great to have representatives from DCIT, from EPSIRC, from Wicker here, as well as the university teams who've been having stands in the refectory. So thank you very much, everyone, for everyone who's helped put this together. So thank you very much indeed. So I think now the plan is I'm going to hand the microphone over to Sheetal, who's coming to the front as chairing today our external advisory board. And Sheetal, I think, might say a couple of words, and then I'm going to hand over to Sheetal and our representatives to do the prizes with the Bragg team, and I'm not going to make a mess of it. So Sheetal, it's over to you.
Thank you very much, Edmund. I don't know what to say, what more to add to what Edmund's done. First of all, I also want to echo my thanks to the whole team for putting this together. I've been involved in Bragg for 8 years, I think, before Bragg was Bragg. And every year, I'm blown away by not just the quality of the speakers at the Exchange, but also the speakers we have at the PhD Symposium, but also the diversity. You know, I've learned, well, I don't think I have learned about chiral phonons, but Edmund said he would teach me sometime, but I'll be busy that day when he asks me to. But, you know, we've gone right from mathematical modeling through physics, through engineering to biology. And what's been really interesting has been how all of those disciplines are coming together, and we see that in the Bragg. So it's been fantastic. And, you know, every year it gets better and better. So next year there's a lot to look forward to. So thank you to all the speakers over the 2 days. Actually, it's been 2 really easy days to attend. Usually by the end of the first day on a conference, you're thinking, I need a glass of wine or a bottle of whiskey, but it's been really good. I've really enjoyed every single moment. So thank you, everybody. Thank you for staying till the end. I'm not going to say any more. We'll do the prizes.
We're going to do prizes, yes.
Yeah.
You want to start with posters? Right. I need some help. Yes. Right.
I did sign lots of things.
Sorry, just 1 second. Yes. Kay, do you want to say? We're going to do the posters first, and Kay from RSC is going to say a few words, I think.
Hello, everybody. Can you hear me okay? Amazing. So my name is Kay Burrows. I'm here from the Royal Society of Chemistry. I am the Deputy Editor for Soft Matter, but I'm also here representing Molecular Systems Design and Engineering, Materials Horizons and Materials Advances, who've sponsored the poster prizes. This is the 2nd year that I've been to the Bragg Exchange, and I go to a lot of conferences, and this is one of my favourites, partly because it is in Leeds. I did my PhD here. But I just think it's great. As Sheetal was saying, you know, we've gone from solid-state NMR to lateral flow tests, and I just think it's really cool. So thank you for having me. Are we ready to do the formal? Yeah.
You shouldn't be doing so.
All this technology and we're stymied by paper. Thank you very much. Okay, so the first runner-up poster prize goes to Serafina Coupe from the School of... Serafina is from the School of Electronic and Electrical Engineering, and the poster was DNA origami for single molecule biosensing. Okay, so the second runner-up poster prize goes to Bianca Hast from the School of Food Science and Nutrition for the poster Designing Bio-Inspired Microgels for Enhanced Mucosal Adhesion. And then the best poster prize of £150 goes to Charlotte Wyatt from the School of Chemistry. And this poster was, how does macromolecular crowding influence SIF formation? Thank you, everyone. I will hand this back to you.
Well, that's a very dangerous thing to do, but thank you very much as well for the Royal Society of Chemistry for their support. It's really good, and thank you so much for coming as well for the conference. It's really, that's a pleasure. Okay, and then we've got the best of the short talks, and this is going to be presented by Edward Rush from Space Hub Yorkshire, and I'm going to hand over to you, and I don't know if you want to say a couple of words or not.
Yeah, thank you. I'll briefly introduce Space Hub Yorkshire, what we do and who we are for those of you who don't know. So my name's Ed. I'm the network coordinator for a UK Space Agency funded project managed by Space Hub Yorkshire called UK EONS. So my interests are primarily in Earth observation, but Space Hub Yorkshire are very well engaged with a radio frequency cluster based in Yorkshire. So if anyone has career aspirations or, say, business engagement aspirations in radio frequency and waveforms and technology that I don't fully understand. I like cameras that use optics and look at things, so it's all very visual. So anything beyond that is way over my head. But Space Hub Yorkshire is an industry body. Our role is to try and help grow the space sector in Yorkshire. So anything we can do to help that is always what we're trying to do. And if anyone's got any ideas or wants to engage with us, please reach out at the end, and I'm more than happy to have a chat with you and go through things from there. But yeah, I think we're on to the prizes. Awesome, thank you very much. So we had 6 early career researcher talks from four schools across the Faculty of Engineering and Physical Sciences and the Faculty of Medicine and Health. The best talk prize is kindly sponsored by Space Hub Yorkshire, thank you, with the winner receiving £250. We're just doing one prize, aren't we? Yes. Yeah. So the best early career researcher talk goes to Andrea Laybourn from the School of Chemistry for their talk on porous materials in the pipeline, optimising metal organic frameworks in flow.
will pass it on to her later. But, okay.
Awesome.
Thank you, sir. Thank you. Thank you. And can I just say a big thank you to all the people who presented and all the posters. They were really excellent. So thank you very much for everyone who's prepared talks and posters. Really good exchange. And thank you all very much. And if you're travelling away from Leeds, have good journeys home as well. So thank you all very much indeed.